Hey everyone, welcome to the course on modern JavaScript. Get ready to explore the essentials of this dynamic language, from its syntax and features to advanced concepts like modules, classes, and asynchronous programming. You'll gain hands-on experience through coding exercises, enhancing your skills in building efficient and organized web applications. Plus, don't forget to check out the GitHub repository linked in the description for all the code examples we'll cover. If you're excited about diving deeper into JavaScript, hit that subscribe button and join our community. Now, let's get started. JavaScript has been around for many decades now and has undergone multiple revisions. It's an incredibly versatile language that has evolved significantly since its inception, shaping the way we build web applications today. This introduction to modern JavaScript will take you through its evolution, key features, and practical examples to help you grasp the fundamentals and begin your journey into the modern JavaScript world. In this section, we delve into the modularity introduced by ES6, exemplified through the creation of a simple math module. The math.js file illustrates how to define a function, add, which takes two parameters and returns their sum. This export mechanism allows the add function to be made accessible outside the module, promoting code reuse and organization. Next, in the main.js file, we see how to import this function using the import statement, specifying the path to the math.js module. This showcases the modular architecture, enabling separation of concerns, where logic is broken down into distinct files. By invoking add_3, the code demonstrates the function's ability to compute the result and display it in the console. This clear organization not only enhances readability, but also makes it easier to maintain and scale projects as they grow. Embracing this modular approach is essential for any aspiring developer looking to write efficient and clear JavaScript code. In this section, we delve into the creation of a simple class to represent a person in JavaScript. The person class encapsulates two primary properties, name and age, which are initialized through the constructor method when a new instance is created. This constructor establishes the foundation for our object, allowing us to assign values to these properties at the time of instantiation. Inside the class, we also define a method called greet. This method serves to showcase the characteristics of the person through a console log statement, effectively demonstrating how to use both properties in a practical context. When we instantiate a new person object, like John, using the class constructor, we provide it with specific values for name and age. Invoking the greet method on our John instance reveals how the class structure promotes organization and reusability in our code. By defining a class, we facilitate easy creation of multiple objects with shared behaviors, thereby enhancing code clarity and maintainability. This approach exemplifies modern JavaScript's capabilities, making object-oriented programming more accessible and streamlined. In this section, we explore the practical application of arrow functions through a simple example involving arrays. We start with an array of numbers, and our goal is to create a new array that contains the squares of these numbers. Initially, we utilize a regular function with the map method to achieve this transformation. This traditional approach requires more syntax, making it slightly less concise. The map method is called on the numbers array, passing a function that takes each number and returns its squared value. However, we then optimize the code by using an arrow function. Arrow functions provide a more succinct syntax, allowing us to express the same logic with less code. In this instance, we simply write num equals num, capturing the essence of the operation without the need for the function, keyword, or braces, thanks to the implicit return feature. Both methods produce the same result, but the arrow function demonstrates a more modern and readable approach in JavaScript. This showcases how arrow functions streamline code and improve readability while maintaining the functionality of traditional function expressions. Template literals are a powerful feature in modern JavaScript that enhance the way we create strings. In this example, we declare a variable called name and assign it the string Alice. The real magic happens when we create another variable, greeting, using backticks to define a template literal. This allows us to embed the name variable directly within the string using the syntax. Rather than using cumbersome string concatenations, template literals simplify the process of combining variables and strings. The line with the console log statement then outputs a personalized greeting, showcasing how template literals can produce dynamic and readable strings. This approach not only cleans up the code, but also makes it much easier to read and understand, especially when working with longer strings or when incorporating multiple variables. By leveraging template literals, developers can create more maintainable and expressive code that aligns with the contemporary JavaScript practices introduced in ES6. The spread operator is a powerful feature in modern JavaScript that allows you to easily merge arrays. In the example provided, we have two arrays, R1 and R2. By utilizing the spread operator, we can expand both arrays into individual elements and combine them into a new array called combined. This approach makes the merging process concise and efficient, resulting in a single array that contains all elements from both R1 and R2. When we log combined to the console, we see all the elements in a seamless list. Next, we delve into destructuring assignment, which simplifies the process of extracting values from objects. In the example, we have an object representing a person with properties like name and age. Instead of accessing these properties individually, destructuring allows us to unpack them into distinct variables in a single line. This enhances code clarity and reduces redundancy. By directly accessing name and age from the person object, we streamline our code while maintaining readability, making it easier to manage and understand. In this part of modern JavaScript, we explore the async await syntax, which simplifies the way we handle asynchronous operations. The async keyword is used to define an asynchronous function, indicating that this function will return a promise. Within this function, we employ the await keyword to pause execution until a promise is resolved, allowing us to write cleaner code that resembles synchronous programming. In the provided code, the fetchData function makes a network request to retrieve data from a specified API. The await fetch https://API example com/data line pauses the function execution until the fetch call is completed, which helps in managing asynchronous events more intuitively. If the fetch is successful, the response is paused as JSON, and the resulting data is logged to the console. However, should any errors occur during this process, the try-catch block catches those errors and logs an error message to the console. This approach not only streamlines error handling, but also significantly reduces the complexity traditionally associated with callbacks, making the asynchronous code easier to read and maintain. In conclusion, modern JavaScript offers a plethora of features that enhance productivity, readability, and maintainability of code. From modular programming to async functionality, these updates have redefined how developers build applications on the web today. Embracing these modern features will not only help you code more efficiently, but also prepare you for the vast landscape of frameworks and libraries built on top of JavaScript. Remember, the journey of learning modern JavaScript has just begun, and there's so much more to explore. So, roll up your sleeves and dive into the exciting world of modern JavaScript. Modules allow us to separate our application code into independent units, each containing code for one aspect of functionality. This modular approach not only makes our code cleaner and more organized, but also promotes reusability and ease of maintenance. So far, we learned about the evolution of JavaScript, starting from its creation in 1995 and the introduction of ECMAScript, which significantly enhanced its capabilities. Modern JavaScript features such as modules, classes, arrow functions, template literals, and the spread operator have improved code organization and readability. We also explored asynchronous programming with async await, making it easier to handle complex operations. Overall, these advancements have transformed JavaScript into a powerful language for building dynamic web applications. Now, we will talk about modules and imports, diving deeper into how they enhance our coding experience. In this section, we will explore the implementation of addition and subtraction modules designed for a simple calculator application. The add.js file defines a function named add, which takes two parameters, a and b, and returns their sum. It uses the export keyword, making this function available for use in other modules. This modular approach allows us to encapsulate functionality, thereby keeping our code organized and focused. Similarly, in the subtract.js file, we see the creation of a subtract function that also takes two parameters and returns the result of subtracting b from a. Just like the addition function, it is exported for external access. By defining each mathematical operation in its own module, we achieve a clean separation of concerns, enhancing code maintainability. Together, these modules exemplify the power of JavaScript modules to isolate functionality, promote code reusability, and streamline development. Such a structure not only makes the application easier to manage, but also simplifies the process of expanding its features in the future. In this section, we are combining our previously created modules to build a simple calculator functionality using JavaScript. Here, we start by importing the add function from add.js and the subtract function from subtract.js, enabling us to utilize these operations within our calculator. The import statement is crucial as it allows us to access the functionalities defined in separate modules, which is a core principle of modular programming. After importing, we execute the add function with the parameters 5 and 3, storing the result in the variable sum. Similarly, we call the subtract function with the same parameters, assigning the result to the variable difference. This structured approach not only organizes the code better, but also promotes reusability. We can easily manipulate and log the results by printing them to the console, demonstrating how our modularized code can effectively implement basic arithmetic operations. Lastly, if we need additional operations, we can seamlessly integrate them by creating new functions in their respective modules, enhancing our calculator's capabilities without cluttering the main file. In this section, we dive into how modules in JavaScript help manage naming conflicts and improve code organization. We have two modules, multiply.js and multiply from another source.js, both defining a multiply function. However, each function has its own unique behavior. The multiply function in multiply.js simply multiplies two numbers, while the one in multiply from another source.js adds an offset to the product. In calculator.js, we demonstrate how to import these functions while avoiding naming collisions by using the as keyword to create aliases. The multiply basic alias refers to the basic multiplication function, and multiply with offset refers to the modified function. This technique clarifies which function is being called, especially when the same function name is used across different modules. The resulting output clearly shows the two calculations, with the first returning 12 and the second returning 13. This practice exemplifies the power of module scopes in maintaining clean and conflict-free code as your application expands in complexity, enabling you to introduce more functionalities without confusion. In this section, we are focusing on how the user.js module is structured to manage user data within our application. It starts by declaring an empty array, users, which will hold all user objects created throughout the application's lifecycle. We define two main functions, addUser and getUsers. The addUser function takes a user's name as a parameter, creates a new user object with a unique identifier, and adds it to the users array. This method not only facilitates the addition of users, but also returns the newly created user object, which can be useful for confirming the successful addition or further processing. The getUsers function, on the other hand, provides access to the current list of users. By exporting these functions, we are allowing other modules to interact with the user data without directly manipulating the internal state of the user.js module. This encapsulation ensures that our code retains a clear structure and promotes better management of dependencies. By using this module, we can easily scale our application to handle user-related functionalities without cluttering the overall codebase. In this section, we observe how different modules come together to form a cohesive application. The app.js file acts as the main entry point of our application, where we import functions from our order.js module. Here, the createOrder function is invoked to simulate creating an order for a user named Alice, along with the item she orders, a laptop. This demonstrates how we can initiate actions and create records based on user input, leveraging the functionality defined within our module. Following this, we utilize the listUsersWithOrders function to retrieve and display orders associated with the specified item. This showcases the interaction between different modules. While createOrder records a new order, listUsersWithOrders retrieves existing data, thus illustrating the seamless flow of information. By employing modular programming practices, we ensure that each module maintains a well-defined purpose, allowing for easier maintenance and scalability. This structured approach significantly reduces complexity, as it's clear where each piece of functionality resides, ultimately paving the way for future enhancements without disrupting existing code. Next, let's explore the importance of circular dependencies and how to avoid them while using modules. A circular dependency occurs when two modules depend on each other. For instance, if user.js imports something from order.js and simultaneously order.js imports from user.js, it leads to confusion and can cause your application to malfunction. To alleviate this, it's better to structure your modules in a way that dependencies flow in one direction. Always aim for a hierarchy or define the relationship of modules clearly to prevent circular dependencies from arising. For example, if order.js needs specific data validated in user.js, consider creating a third module, perhaps called validation.js, that both user.js and order.js can import from. This reorganization not only prevents circular dependencies from forming, but also encourages cleaner design practices. In this section, we explore the concept of dynamic imports in JavaScript, which allows for more efficient loading of features on demand. The load feature function is defined as an asynchronous function that employs the import method to load the feature.js module. This means that instead of loading all modules at the start, we can wait until we actually need the module, which can significantly enhance performance, especially in large applications. When the load feature function is invoked, it triggers the dynamic import of feature.js, effectively pausing any subsequent code execution until the module is fully loaded due to the await keyword. Once loaded, the feature function, which is expected to be exported from feature.js, is called, ensuring that user interactions trigger the loading of only necessary code. This approach not only reduces initial load times, but also combats unnecessary resource consumption, allowing for a more streamlined user experience. By leveraging dynamic imports, developers can create applications that are responsive and optimized for performance. To wrap things up, understanding modules and imports in JavaScript is crucial for building modern, scalable applications. They promote code organization, prevent naming conflicts, minimize dependencies, and enhance performance through lazy loading. As we've seen, modular programming empowers developers to create maintainable and reusable code, making life easier for you as you embark on your journey of developing dynamic web applications with JavaScript. So roll up your sleeves and get started with modules today, because the possibilities are virtually endless. To prevent any incorrect data from being assigned. This pattern not only safeguards our mileage data, but also centralizes its management within the class, promoting good practices in object-oriented programming. In this example, we demonstrate how inheritance works in JavaScript by creating a vehicle class and a car subclass that extends it. The vehicle class encapsulates a private property, license plate, which is initialized via the constructor and can be accessed through the public method getLicensePlate. This encapsulation helps to protect the license plate data from unauthorized access. Moving to the car class, it inherits the properties and methods from the vehicle class while also defining its unique private properties, make and model. The constructor of the car class calls the parent class's constructor using the super function to ensure proper initialization of the license plate. Additionally, the car class introduces its public method, getCarInfo, which utilizes both its private properties and the inherited getLicensePlate method. This design not only promotes code reusability, but also demonstrates how subclasses can extend and modify behaviors provided by their parent classes. After creating an instance of car, we can see how it effectively combines the functionalities of both classes, encapsulating and protecting data while offering a user-friendly interface. In this example, we explore how inheritance in JavaScript allows for more efficient code reuse by creating a hierarchy of classes. We start with the vehicle class, which encapsulates a private property, license plate, ensuring that this sensitive data is only accessible within the class. The getLicensePlate method provides a controlled way to access the license plate information. Next, we introduce the car class, which extends vehicle. This subclass inherits the parent class's properties and methods, while also defining its own private properties, make and model. In the constructor of car, we invoke super license plate to initialize the inherited property before setting the specific attributes of the car. The method getCarInfo is overridden to provide a specialized string that combines the car's make and model with its license plate, showcasing how we can build on the functionality of inherited methods. Overall, this setup demonstrates the key principles of object-oriented programming in JavaScript, including encapsulation, inheritance, and method overriding. In this example, we see the implementation of a car class that utilizes static class members and methods to track the number of instances created. The static property carCount is initialized to 0, and it is incremented within the constructor each time a new car instance is created. This approach allows us to maintain a count of all car objects without needing to reference individual instances. The static method, getCarCount, serves as a utility to access the current value of carCount, enabling us to retrieve the total count of car instances directly from the class itself rather than from an instance. This illustrates the distinction between static and instance members and highlights how static methods can provide a means to share functionality across all instances of a class. Additionally, the getCarInfo method provides an easy way to retrieve the details of each car instance, demonstrating how instance methods operate alongside static features. The final console statement outputs the total number of cars created, effectively showcasing how static members can enhance the functionality and usability of classes in JavaScript. In this segment, we introduce the concept of accessors in our car class, incorporating getter and setter methods for managing private properties effectively. In the class definition, we declare two private fields, make and model, which encapsulate the car's make and model. The constructor initializes these fields with values, ensuring data integrity. We then implement a getter for the make property, allowing external code to retrieve the make of the car without directly accessing the private field. This not only promotes encapsulation, but also maintains control over how information is accessed. Meanwhile, the setter for model enables controlled modification of the model property. By using this setter, users can update the model while still respecting the encapsulation principles. This design pattern keeps the internal data protected, reducing potential misuse while providing a clear and user-friendly interface. Finally, the getCarInfo method returns a formatted string, showcasing both the car's make and model together. Overall, this approach exemplifies good practices in object-oriented programming, resulting in clean and maintainable code. Now, it's essential to remember that with great powers come great responsibilities. While private members add a layer of security to your class properties, excessive use can lead to less readable code. It's all about finding that balance and ensuring your class design is clear and purposeful. Understanding when to use public members versus private is crucial in maintaining a clean architecture and ensuring your code stays maintainable and scalable. As we wrap up this section on advanced class features, it becomes clear that modern JavaScript offers robust tools to create structured and secure classes. Public and private class members provide flexibility in how we manage data, while inheritance supports efficient code reuse. Combining these elements with static methods and accessors paves the way for powerful and maintainable code. So, if you're looking to write clean and effective JavaScript, always keep these principles in mind. Understanding advanced class features will undoubtedly enhance your coding skills and empower you to tackle more complex projects with confidence. Happy coding! Design patterns are reusable solutions to common software design problems that can help us create more efficient, maintainable, and scalable code. Today, we'll dive deep into the world of design patterns, specifically focusing on their categories, which include creational, structural, and behavioral patterns. So far, we learned about the importance of safeguarding data using private members in classes and how inheritance allows one class to extend the properties and methods of another, facilitating code reuse. We explored creating a base class, vehicle, and derived classes like car, utilizing methods like super for managing shared functionality. Additionally, we discussed the role of static methods for utility functions and the implementation of accessors to manage private properties while maintaining a clean interface. Overall, these advanced class features enhance our ability to write structured, maintainable, and secure JavaScript code. Now, we will cover the fundamental concepts of design patterns, focusing on the three main categories: creational, structural, and behavioral patterns. In this section, we implement the factory method pattern, which allows for creating different types of vehicles through a single interface without specifying the exact class of object that will be instantiated. We start by defining a base class, vehicle, that encapsulates common properties such as type, which can be extended by specific vehicle classes like car and truck. Each subclass initializes its type accordingly, promoting code reuse through inheritance. The key component, vehicle factory, includes a createVehicle method. This method employs a switch statement to determine the type of vehicle to create based on the provided input, effectively centralizing the object creation logic. This decoupling means that adding new vehicle types later will require minimal changes to existing code, aligning with the open-closed principle, which advocates for extending classes without modifying them. Finally, we showcase how to use the factory to create a car instance, demonstrating the simplicity and flexibility offered by this design pattern, which ultimately makes our code cleaner and more maintainable. The singleton pattern is designed to ensure that a class has only one instance and provides a global point of access to that instance. In the provided JavaScript implementation, the constructor checks if an instance of the singleton class already exists. If it does, the constructor returns that instance instead of creating a new one. This is achieved by storing the instance in a static property. The class also includes methods to manipulate shared data, namely, add data and get data. When you create multiple instances of the singleton, you end up with the same instance each time, as seen when we add different items through singleton1 and singleton2. Despite adding item1 and item2 through different variable references, both log statements reveal that the shared data array maintains the state consistently, showcasing the essence of state management in a singleton. This pattern is particularly useful for situations like managing global settings or logging, where a single instance is crucial for maintaining coherence across various parts of an application. In this section, we will examine the builder pattern, which provides a flexible and readable way to create complex objects. The implementation starts with the car class, which initializes the attributes brand, engine, and wheels with default values. To construct a car object more efficiently, we introduce the carBuilder class. This builder encapsulates the creation logic and allows for a step-by-step configuration of the car. Each method in the carBuilder, setBrand, setEngine, and setWheels, is designed to modify a specific property of the car. Importantly, each method returns the carBuilder instance itself, enabling method chaining for more concise and readable code. This chaining allows developers to easily set multiple attributes in a single statement, enhancing maintainability. Finally, the build method creates and returns the fully constructed car object. The usage example demonstrates how to utilize the builder to create a car with specific attributes in a fluid manner. This approach becomes particularly beneficial when dealing with many optional parameters, simplifying object construction while maintaining clear code structure. The adapter pattern facilitates communication between incompatible interfaces, allowing two systems to work together seamlessly. In this implementation, we define a legacy system class with a method that provides data from an older system. Similarly, the new system class presents a specific request method for modern functionality, but these two systems cannot interact directly due to differing interfaces. To bridge this gap, the adapter class is introduced, which takes an instance of new system in its constructor. The adapter class provides a unified method called request that translates calls made to it into compatible requests that the new system can understand. By doing so, it effectively allows legacy components to access new functionalities without requiring any modifications to the existing systems. Lastly, we illustrate the usage by creating instances of both systems and the adapter. By calling the request method on the adapter, users can seamlessly access data from the new system, while legacy system calls remain intact. This approach promotes code reuse and flexibility, showcasing how the adapter pattern elegantly resolves interface incompatibility. In this section, we delve into the bridge pattern, which distinguishes an object's interface from its implementation, allowing both to evolve independently. Here, we define a shape class that serves as an abstract representation of shapes. It accepts a drawAPI parameter, which manages the drawing strategy. This decoupling permits various drawing implementations without impacting the shape class itself. The circle class extends the shape class, adding specific properties like radius. Inside its draw method, it first logs details about the circle and then calls the inherited draw method, which leverages the provided drawAPI to perform the drawing operation. The drawAPI class provides a concrete implementation of the drawing mechanism, encapsulating the specific details of how a shape is drawn. This design pattern promotes flexibility and scalability, as new shapes or drawing methods can be introduced without modifying existing code. By adhering to the bridge pattern, we enhance our codebase's maintainability, allowing for more straightforward adaptations to changing requirements while keeping implementation concerns separated. This structure ultimately leads to cleaner and more manageable code in complex systems. In this implementation of the composite pattern, we define a structure for graphics where both individual shapes and compositions of shapes behave uniformly. The graphic class serves as an abstract base class, laying the groundwork for the structural components of our graphic representations. It contains a draw method that must be implemented by subclasses, enforcing a contract for all graphic elements. The circle class extends graphic and provides a concrete implementation of the draw method, allowing it to output a simple message indicating that it is drawing a circle. The more complex composite graphic class also inherits from graphic and introduces a collection for managing multiple graphics, allowing for the creation of hierarchical structures. With its add method, composite graphic can accept individual graphic objects, making it possible to build nested compositions seamlessly. In its implementation of the draw method, the class iterates over its collection of graphics and calls their respective draw methods. This design demonstrates how individual objects and their compositions can be treated uniformly, promoting flexibility and reusability in managing graphic objects. The practical usage at the end showcases how easily we can create a composite of circles and draw them collectively, highlighting the effectiveness of the composite pattern in structuring complex object relationships. In this section, we'll delve into the implementation of the observer pattern, which is crucial for creating a responsive and event-driven architecture. The subject class serves as the focal point of the pattern, maintaining a list of observers that are interested in changes to its state. When an observer is added using the attach method, it is stored in the observers array. Whenever the state of the subject changes, it can invoke the notify method, which iterates through all attached observers, calling their update method and passing a message that captures the change. This ensures that all observers are updated simultaneously, promoting loose coupling between the subject and its observers. The observer class represents the entities that react to changes in the subject. It has a constructor that takes a name for identification and an update method that defines how it responds to notifications. This separation allows different observers to implement their response logic independently. In the usage example, we create a subject and two observers, demonstrating how a message sent from the subject triggers responses from each observer, highlighting the effective communication established through this pattern. In this section, we explore the command pattern, which encapsulates requests as objects, providing greater flexibility in handling operations. Here, we define a base command class with an execute method that subclasses must override, ensuring a consistent interface for executing commands. The light class represents the receiver, containing methods to turn the light on or off. We then create two command classes, lightOnCommand and lightOffCommand, that extend the command class. Each of these command classes takes a light object as a parameter and implements the execute method to trigger the respective action on the light. To demonstrate the pattern, we instantiate a light object, along with two command objects for turning the light on and off. By calling execute on each command object, we can control the light's state without needing to reference the light class directly. This decoupling of the command invocation from the light manipulation enhances the system's flexibility, allowing for easy extensions, queuing of requests, or logging of actions in a larger application context. The strategy pattern allows us to define a family of algorithms, encapsulate each one, and make them interchangeable at runtime. In the provided code, we start by creating an abstract class called sortStrategy, which contains a method sort that will be overridden by specific sorting algorithms. This design ensures that any class extending sortStrategy must implement its own sorting logic. Next, we have two concrete classes, BubbleSort and QuickSort, each implementing the sort method in their unique way, allowing them to output which algorithm is being used. The main functionality is managed by the sortContext class, which takes a sorting strategy upon initialization. By using the setStrategy method, users can change the sorting algorithm dynamically, promoting flexibility and allowing the same context to manage different sorting behaviors without modifying the underlying code. This setup portrays how the strategy pattern fosters clean code practices by adhering to the open-closed principle, allowing the code to be open for extension, yet closed for modification, ultimately simplifying the task of integrating new algorithms in the future. In summary, design patterns are an integral part of software design, allowing developers to create robust, flexible, and maintainable systems. We began this discussion by examining the categories of design patterns, including creational, structural, and behavioral. Each category serves a vital role in managing the complexity of software design and architecture. These patterns provide us with essential tools to organize our code efficiently, making it easier to work on large projects and enhancing collaboration among developers. By applying these patterns, we are not only solving specific design problems, but also promoting best practices in programming. As you grow in your programming journey, I encourage you to explore these patterns and consider how they can be applied in your projects, enabling you to write cleaner, more effective code. Creational design patterns focus on handling object creation mechanisms, enabling the creation of objects in ways suitable for specific situations. By leveraging these patterns, developers can enhance code maintainability, scalability, and flexibility while effectively managing how objects are instantiated. So far, we learned about the significance of design patterns as reusable solutions to common software design issues, focusing on categories such as creational, structural, and behavioral patterns. We explored several specific patterns including the factory method, singleton, builder, adapter, bridge, composite, observer, command, and strategy patterns, each serving distinct purposes in managing object creation, composition, and interaction. As we continue, we'll delve deeper into their applications and benefits in real-world projects, particularly focusing on creational design patterns and how they empower object creation in software design. In this section, we will examine the implementation of the factory method pattern through a vehicle creation example. The vehicle class serves as a base class, defining a common interface with a drive method that must be overridden in subclasses. The car and truck classes extend the vehicle class, each providing its own specific implementation of the drive method, enabling different behaviors for each vehicle type. This structure demonstrates polymorphism, allowing different vehicle types to be treated uniformly while maintaining their distinct functionalities. Next, we encounter the vehicle factory class, which centralizes the object creation logic. The createVehicle method takes a type, parameter, and returns a new instance of either the car or truck class based on the provided input. This approach hides the instantiation details from the client code, allowing for a clean separation of responsibilities. Finally, we see the usage of the factory, where an instance of vehicle factory is created. The client calls the createVehicle method to generate specific vehicle objects, illustrating how the factory method pattern simplifies object creation while enhancing code maintainability and flexibility, making it easy to introduce new vehicle types in the future. In this section, we explore the implementation of the singleton pattern in JavaScript. The singleton class begins by checking if an instance of itself already exists when the constructor is called. If an instance is found, it returns that instance, effectively preventing additional instances from being created. This design ensures that all calls to create an instance of the singleton class will return the same object, maintaining a single point of access throughout the application. Within the class, there is an array called data to store information, manipulated through two methods. addData, which allows items to be added to this array, and getData, which retrieves the current state of the data. In the usage section, we create two variables, singleton1 and singleton2, both instantiating the singleton class. Adding data to both variables demonstrates that they reference the same underlying object, evidenced by their identical output when invoking the getData method. Additionally, the comparison of both instances confirms their equivalence, embodying the essence of the singleton pattern by managing shared resources efficiently. In this section, we explore the builder pattern through the implementation of a car builder. The car class serves as a blueprint for car objects, defining properties such as brand, engine, and wheels. The real magic happens in the car builder class, which encapsulates the construction logic, allowing users to create a car object step by step. Each method in the car builder, setBrand, setEngine, and setWheels, modifies the corresponding property of the car instance and returns the this context. This method chaining capability enables a fluent interface, making it intuitive to specify multiple attributes in a single statement. The final call to the build method returns the constructed car object. This approach separates the object creation from its representation, making it particularly useful when dealing with complex objects that require specific combinations of attributes. By using the builder pattern, developers can create flexible and readable object construction processes, enhancing maintainability in applications with numerous configuration options. In this section, we will examine the prototype pattern, which is integral for creating new objects by copying existing ones instead of constructing them from scratch. The prototype class demonstrates this concept through its constructor, which initializes an object with a name property. The key feature here is the clone method, which facilitates object duplication. When called, it returns a new instance of the prototype class, effectively creating a copy of the original object while maintaining the name. After defining the prototype, we showcase its usage by instantiating an object called original with the name original. We then create another object, clone, by invoking the clone method on the original instance. This duplication allows us to manipulate the cloned object independently from the original. Using console log, we can verify that while both objects share the same name, they are indeed different instances, as confirmed by comparing their references. This pattern is particularly advantageous when object creation is resource-intensive, offering a performance-efficient way to generate new instances by leveraging the cloning of existing ones. In the abstract factory pattern implementation shown, we see a neat structure for creating user interface components tailored to different operating systems. The Windows button and Mac button classes exemplify how specific button types are defined, each with their own rendering method that outputs a message indicating which type of button is being rendered. The button factory class is crucial here as it encapsulates the logic for creating these button instances. By providing a create button method, it allows clients to request a button for a specific operating system without needing to know the details of the button classes. The logical flow inside create button uses conditional statements to return the corresponding button type based on the operating system input. This approach emphasizes flexibility. Should a new button type be needed in the future, we can simply add a new class and extend the factory method accordingly. Finally, the example also includes usage of the button factory, demonstrating how a client can easily create a macOS button and render it. This encapsulation streamlines the creation process, promotes code reuse, and adheres to the open-closed principle, ensuring that existing code remains unmodified even as new requirements emerge. With these diverse creational design patterns, developers have powerful tools at their disposal to enhance the flexibility and maintainability of their code. From managing complex object creation with the factory and builder patterns to encapsulating families of related objects with the abstract factory pattern, understanding these patterns will ultimately lead to more robust software development practices. As we explored creational design patterns, we saw how each pattern serves unique purposes, addressing various challenges in object creation. We've examined how encapsulating the creation logic gives developers an edge in maintaining code quality and adapting to new requirements with ease. So, now that we've covered a broad range of creational design patterns, you're equipped with knowledge that will elevate your ability to design and implement scalable systems. In your coding journey, remember to consider these patterns as solutions to specific problems you'll encounter while building applications. By employing these creational design patterns, you not only make your code cleaner and more efficient, but also enhance your ability to collaborate effectively with other developers. Design patterns are not just theoretical concepts, they are practical tools that, when applied correctly, significantly improve the overall architecture of your projects. Thank you for joining this lesson on creational design patterns, and I hope you feel inspired to dig in and apply what you've learned in your next coding adventure. Behavioral design patterns focus on improving or streamlining the communication between disparate objects in a system. They help simplify object interaction while ensuring that they remain loosely coupled. This makes systems easier to understand and modify. So far, we learned about several creational design patterns, including the factory method, singleton, builder, and abstract factory patterns, which focus on optimizing object creation and promoting code flexibility. Each pattern provides unique strategies for handling object instantiation, allowing for better management of resources and enhancements in software scalability. We've discussed how these patterns encapsulate creation logic to improve code maintainability and facilitate the addition of new features. As we progress, we'll delve into behavioral design patterns, exploring how communication and responsibilities are managed among different objects in our software systems. In this implementation of the chain of responsibility pattern, we create a framework for handling support requests through a hierarchy of handlers. The support handler class establishes a base for all handlers, introducing methods for setting the next handler in the chain and handling incoming requests. Each specific handler, receptionist, technician, and manager inherits from support handler and overrides the handle method to determine if they can process a particular request based on its complexity level. If a handler deems a request beyond its capacity, it forwards the request to the next handler in the chain, allowing for a seamless flow of responsibility until a suitable handler is found or the request reaches the end of the chain. The code exemplifies how we can create a dynamic support system using instances of these handlers, which are linked together. Through this design, adding more levels of support becomes straightforward, as new handlers can be introduced without altering the existing structure. This enhances code maintainability and scalability, demonstrating the benefits of employing the chain of responsibility pattern in software design. In this implementation of the observer pattern, the weather station class serves as the subject that maintains a list of observers interested in temperature changes. It allows observers to register or unregister themselves through the addObserver and removeObserver methods. When the temperature is updated using the setTemperature method, the weather station automatically notifies all registered observers by invoking their update methods. This notification mechanism ensures that any changes in the weather data are promptly communicated to the observers without tightly coupling them to the weather station. The temperature display and alert system classes act as concrete observers. The temperature display simply outputs the current temperature to the console whenever it receives an update, thus reflecting real-time changes in a user-friendly manner. Conversely, the alert system checks if the temperature exceeds a specific threshold and raises an alert if it does, demonstrating how different observers can respond differently to the same event. This design facilitates easy addition or removal of observers without needing to alter the weather station's core functionality, promoting flexibility and maintainability in the system. In this section, we explore the implementation of the strategy pattern through a navigation application that selects different methods for calculating routes based on user preferences. The core component is the route strategy class, which serves as a base class for various specific strategies, such as walking strategy, driving strategy, and biking strategy. Each of these derived classes implements the calculateRoute method, providing tailored responses for the respective transportation modes. The Navigator class plays a crucial role by holding a reference to a selected strategy. Through the setStrategy method, the user can dynamically choose which route calculation strategy to employ. When a user calls the Navigate method, the selected strategy's calculateRoute function is invoked, facilitating the desired route computation. This structure clearly showcases the flexibility of the strategy pattern. Different routes can be calculated without altering the Navigator class itself. Overall, this implementation enhances maintainability and scalability, allowing for the easy addition of new navigation strategies without disrupting the existing codebase. The command pattern is implemented here to encapsulate requests as objects, enhancing flexibility and maintainability. The command class serves as a base class with an execute method, which is overridden by specific command classes. The light class simulates a light fixture, providing methods to turn the light on or off with appropriate console messages. Light on command and light off command extend the command class, encapsulating the actions of turning the light on and off, respectively. Each command takes a light object as an argument in its constructor, ensuring it can invoke the desired actions on the correct receiver. This decoupling of the command objects from the actual light manipulation allows for easy addition of new commands in the future, should we want to incorporate features like undo functionality. The remote control class acts as the invoker, which submits commands to be executed. In the usage example, instances of light, light on command, and light off command are created. By submitting these commands through the remote control, we effectively control the light without directly coupling our control logic with the receiver functions. This encapsulation leads to a more modular design that is easier to manage and extend. In this section, we explore the implementation of the mediator pattern through a chat application. The chatroom class acts as the mediator, managing user registration and facilitating communication between users. When a user registers, their instance is stored in the user's object, along with a reference to the chatroom itself, allowing them to send messages without directly interacting with other users. The send method within the chatroom class handles message delivery. If a specific recipient is provided, the message is sent directly to that user, invoking their receive method. Conversely, if no recipient is specified, the mediator broadcasts the message to all registered users, ensuring that everyone except the sender receives the communication. This design promotes loose coupling among users, simplifying the management of interactions and making it easier to extend functionalities, such as adding new features or enforcing rules. The user class encapsulates the properties and behaviors of individual users, including the ability to send messages and receive them. By communicating through the chatroom, users maintain independence from one another, which ultimately leads to a more maintainable and flexible codebase. In this section, we implement the iterator pattern to manage a collection of books efficiently. The book collection class serves as our main collection management structure, encapsulating an array called books that stores the individual book entries. Additionally, it provides an add book method, allowing us to easily append new titles to the collection. A key feature is the getIterator method, which creates and returns an instance of the book iterator, ensuring we can traverse the collection without exposing its internal representation. The book iterator class plays a vital role in providing sequential access to the books. It maintains a reference to the book collection and an index to keep track of the current position within that collection. The hasNext method checks if there are more books to iterate over, promoting safe traversal. When the next method is called, it retrieves the current book and advances the index, thereby facilitating a step-by-step navigation through the collection. This design adheres to encapsulation principles, allowing users to interact with the collection while keeping the details of storage hidden from them, enhancing the maintainability and flexibility of the code. As we've journeyed through several behavioral design patterns, it's clear that they play a crucial role in managing interactions among objects effectively. Starting from the chain of responsibility and observer patterns to strategies, commands, mediators, and iterators, these patterns demonstrate various methods of decoupling and improving the communication between disparate components. Behavioral design patterns empower developers with the ability to create flexible, maintainable, and scalable systems by optimizing interactions across numerous objects. They not only enhance code clarity, but also facilitate the addition of new behaviors and functionality with minimal impact on existing structures. Through these discussions and code examples, I hope you've gained insights into how to implement and leverage behavioral design patterns in your software projects. By employing these strategies, you can develop robust applications that adapt effortlessly to changing requirements and encapsulate behaviors efficiently. Thank you for joining me in exploring the fascinating world of behavioral design patterns. This video introduces you to the fascinating world of design patterns. Gaining an understanding of these patterns can significantly enhance your software design process, making your applications more efficient and easier to maintain. So far, we learned about behavioral design patterns that enhance communication between objects while keeping them loosely coupled for better maintainability and scalability. We've explored several patterns including chain of responsibility, observer, strategy, command, mediator, and iterator, each offering unique strategies for managing interactions and responsibilities. These patterns empower developers to create flexible and adaptable systems, facilitating changes with minimal impact on existing code. As we continue, we will deepen our understanding of these concepts and how they apply practically within software development. In this section, we'll explore a practical implementation of the factory method pattern using JavaScript. The code begins with the definition of a car class, which represents a car object. This class has a constructor that initializes the car's make and a method called display that returns a string representation of the car's make. Next, we introduce the carFactory class, which serves as a factory for creating car instances. It contains a static method named createCar, which accepts a make as an argument and returns a new instance of the car class. This separation of object creation from the actual use of objects exemplifies a key principle of the factory method pattern. It decouples the instantiation process from the code that will use the created objects. Finally, the code demonstrates its usage by calling the factory method to create a car with the make Toyota, and then invokes the display method on this car instance to output its make. This elegant design allows for easy extension in the future, enabling the addition of new car types without altering existing code, thereby adhering to solid software design principles. In this section, we will explore the implementation of the decorator pattern, which allows us to enhance the functionality of our objects without changing their structure. We start with a base class called coffee, which defines a method to return the cost of a basic coffee. Next, we introduce the milk decorator and sugar decorator classes. Each of these decorator classes takes an instance of the coffee class as a parameter and adds its own cost to the original coffee price. The milk decorator adds an additional $1 for milk, while the sugar decorator adds 50 cents for sugar. This design approach enables us to stack decorators dynamically, showcasing the flexibility of the pattern. In the usage example, we first create a coffee object, then wrap it with the milk decorator, and subsequently with the sugar decorator. Finally, when we call the cost method on our decorated coffee instance, it accurately computes the total price by summing up the base cost and the additions from the decorators, demonstrating the powerful capability of the decorator pattern to extend object behavior in a modular way. In this example of the chain of responsibility pattern, we establish a framework for handling requests through a series of linked handlers. The handler class serves as a base class that introduces the concept of a successor, allowing each handler to either process a request or pass it on to the next handler in the chain. This decoupling is vital for flexibility, enabling changes in the chain without much impact on the request senders. Next, we have two concrete handlers, concrete handler A and concrete handler B. Each handler overrides the handle request method to provide specific logic for processing requests. If concrete handler A receives a request labeled A, it successfully processes it, while any other request is passed to its successor for further handling. Similarly, concrete handler B responds to requests labeled B. This structure ensures that a request progresses through the chain until handled appropriately, demonstrating how responsibilities can be shared among different objects without creating tight coupling. The final usage showcases how to link the handlers and process various requests, highlighting the pattern's scalability and effectiveness in managing object interactions. In conclusion, design patterns provide reusable solutions to common problems in software design. They help ensure that code remains organized, flexible, and maintainable over time. Whether you are creating, structuring, or managing communications between objects, these patterns are invaluable tools in your developer toolkit. As we move forward in our lessons, keep in mind the significance of these patterns. They may seem abstract at first, but their practical applications will soon become apparent as we delve deeper into real-world examples and projects. So, what will we cover next? We will explore individual design patterns in greater detail, providing specific implementation scenarios and showing how they can be combined to solve complex design problems. Stay tuned as we continue uncovering the powerful realm of design patterns. The adapter pattern facilitates communication between incompatible interfaces, allowing two systems to work together seamlessly. In this implementation, we define a legacy system class with a method that provides data from an older system. Similarly, the new system class presents a specific request method for modern functionality, but these two systems cannot interact directly due to differing interfaces. To bridge this gap, the adapter class is introduced, which takes an instance of new system in its constructor. The adapter class provides a unified method called request that translates calls made to it into compatible requests that the new system can understand. By doing so, it effectively allows legacy components to access new functionalities without requiring any modifications to the existing systems. Lastly, we illustrate the usage by creating instances of both systems and the adapter. By calling the request method on the adapter, users can seamlessly access data from the new system, while legacy system calls remain intact. This approach promotes code reuse and flexibility, showcasing how the adapter pattern elegantly resolves interface incompatibility. In this section, we delve into the bridge pattern, which distinguishes an object's interface from its implementation, allowing both to evolve independently. Here, we define a shape class that serves as an abstract representation of shapes. It accepts a drawAPI parameter, which manages the drawing strategy. This decoupling permits various drawing implementations without impacting the shape class itself. The circle class extends the shape class, adding specific properties like radius. Inside its draw method, it first logs details about the circle and then calls the inherited draw method, which leverages the provided drawAPI to perform the drawing operation. The drawAPI class provides a concrete implementation of the drawing mechanism, encapsulating the specific details of how a shape is drawn. This design pattern promotes flexibility and scalability, as new shapes or drawing methods can be introduced without modifying existing code. By adhering to the bridge pattern, we enhance our codebase's maintainability, allowing for more straightforward adaptations to changing requirements while keeping implementation concerns separated. This structure ultimately leads to cleaner and more manageable code in complex systems. In this implementation of the composite pattern, we define a structure for graphics where both individual shapes and compositions of shapes behave uniformly. The graphic class serves as an abstract base class, laying the groundwork for the structural components of our graphic representations. It contains a draw method that must be implemented by subclasses, enforcing a contract for all graphic elements. The circle class extends graphic and provides a concrete implementation of the draw method, allowing it to output a simple message indicating that it is drawing a circle. The more complex composite graphic class also inherits from graphic and introduces a collection for managing multiple graphics, allowing for the creation of hierarchical structures. With its add method, composite graphic can accept individual graphic objects, making it possible to build nested compositions seamlessly. In its implementation of the draw method, the class iterates over its collection of graphics and calls their respective draw methods. This design demonstrates how individual objects and their compositions can be treated uniformly, promoting flexibility and reusability in managing graphic objects. The practical usage at the end showcases how easily we can create a composite of circles and draw them collectively. highlighting the effectiveness of the composite pattern in structuring complex object relationships. In this section, we'll delve into the implementation of the observer pattern, which is crucial for creating a responsive and event-driven architecture. The subject class serves as the focal point of the pattern, maintaining a list of observers that are interested in changes to its state. When an observer is added using the attach method, it is stored in the observers array. Whenever the state of the subject changes, it can invoke the notify method, which iterates through all attached observers, calling their update method and passing a message that captures the change. This ensures that all observers are updated simultaneously, promoting loose coupling between the subject and its observers. The observer class represents the entities that react to changes in the subject. It has a constructor that takes a name for identification and an update method that defines how it responds to notifications. This separation allows different observers to implement their response logic independently. In the usage example, we create a subject and two observers, demonstrating how a message sent from the subject triggers responses from each observer, highlighting the effective communication established through this pattern. In this section, we explore the command pattern, which encapsulates requests as objects, providing greater flexibility in handling operations. Here, we define a base command class with an execute method that subclasses must override, ensuring a consistent interface for executing commands. The light class represents the receiver, containing methods to turn the light on or off. We then create two command classes, lightOnCommand and lightOffCommand, that extend the command class. Each of these command classes takes a light object as a parameter and implements the execute method to trigger the respective action on the light. To demonstrate the pattern, we instantiate a light object, along with two command objects for turning the light on and off. By calling execute on each command object, we can control the light's state without needing to reference the light class directly. This decoupling of the command invocation from the light manipulation enhances the system's flexibility, allowing for easy extensions, queuing of requests, or logging of actions in a larger application context. The strategy pattern allows us to define a family of algorithms, encapsulate each one, and make them interchangeable at runtime. In the provided code, we start by creating an abstract class called sortStrategy, which contains a method sort that will be overridden by specific sorting algorithms. This design ensures that any class extending sortStrategy must implement its own sorting logic. Next, we have two concrete classes, BubbleSort and QuickSort, each implementing the sort method in their unique way, allowing them to output which algorithm is being used. The main functionality is managed by the sortContext class, which takes a sorting strategy upon initialization. By using the setStrategy method, users can change the sorting algorithm dynamically, promoting flexibility and allowing the same context to manage different sorting behaviors without modifying the underlying code. This setup portrays how the strategy pattern fosters clean code practices by adhering to the open-closed principle, allowing the code to be open for extension, yet closed for modification, ultimately simplifying the task of integrating new algorithms in the future. In summary, design patterns are an integral part of software design, allowing developers to create robust, flexible, and maintainable systems. We began this discussion by examining the categories of design patterns, including creational, structural, and behavioral. Each category serves a vital role in managing the complexity of software design and architecture. These patterns provide us with essential tools to organize our code efficiently, making it easier to work on large projects and enhancing collaboration among developers. By applying these patterns, we are not only solving specific design problems, but also promoting best practices in programming. As you grow in your programming journey, I encourage you to explore these patterns and consider how they can be applied in your projects, enabling you to write cleaner, more effective code. Creational patterns provide mechanisms to create objects and are crucial for writing flexible, efficient, and maintainable code in JavaScript. These patterns allow developers to handle object creation in a way that suits their needs, whether it's simplifying instantiation, managing dependencies, or maintaining variations of object types. So far, we learned about the importance of design patterns in software development, focusing on behavioral, creational, and structural patterns. We discussed behavioral patterns that enhance object communication and reduce coupling, as well as creational patterns like the factory method that allow for flexible object creation. Additionally, we examined structural patterns such as the decorator pattern, which modifies object behavior without altering the base class. As we progress, we will explore individual design patterns in depth, including their practical applications and integration in real-world scenarios. In this session, we'll dive deep into creational patterns and see how they can be effectively implemented in JavaScript. The factory method pattern provides a robust way to create instances of classes without exposing the instantiation logic to the client. In this example, we begin by defining a base button class that establishes a contract for button behavior with a render method, which subclasses are required to implement. We then create concrete button classes, Windows button and Mac button, each overriding the render method to specify their unique rendering logic. The button factory class centralizes the creation of button instances. Instead of the client needing to know which button class to instantiate, it calls the static method createButton, passing in a type argument. This method uses a switch statement to determine which button to create based on the provided type, returning a newly instantiated object without exposing the underlying creation details to the client code. By doing this, the factory method promotes loose coupling and enhances the maintainability of the code. Finally, in the usage example, we see how easy it is to create a button and invoke its render method, demonstrating the power of this pattern in keeping the client code clean and focused on business logic. In this section, we implement the abstract factory pattern, which allows us to create families of related objects without specifying their concrete classes. The code defines several classes, including button and checkbox, each representing different UI elements with a render method that outputs information specific to the type of button or checkbox being rendered. We have specific implementations for Windows and Mac systems, such as Windows button, Windows checkbox, Mac button, and Mac checkbox. Each of these subclasses overrides the render method, providing detailed console messages that indicate which type of UI component is being rendered. The GUI factory class encapsulates the creation logic for these UI components through a static method called createUI. This method accepts a string parameter that denotes the operating system type. Based on the input, it returns an object containing the appropriate button and checkbox instances for that system. For instance, invoking createUI with Mac will yield a Mac button and a Mac checkbox. This design enhances the system's extensibility. Adding support for a new UI family only requires creating new classes and updating the createUI method, not changing client code. The singleton pattern is a design pattern that restricts a class to a single instance while providing a global access point to that instance. In the provided code, the singleton class is structured such that when a new instance is created, it first checks if an instance already exists. If it does, the constructor returns that existing instance instead of creating a new one. This guarantees that any subsequent attempts to instantiate the singleton class will yield the same instance. The class also features a method called sayHello, which outputs a message, demonstrating that the singleton is functioning correctly. In practice, this pattern is beneficial for managing shared resources, such as configuration settings or logging functionalities, ensuring that these resources remain consistent across different parts of an application. The usage example at the end showcases this principle, as both instance 1 and instance 2 reference the same object, as evidenced by the comparison test that returns true. This implementation is crucial for maintaining a controlled environment where simultaneous access does not create unintended behaviors or discrepancies across the application, cementing the singleton pattern's role in effective resource management. In this section, we delve into the builder pattern, which is ideal for constructing complex objects step by step. Here, we define a computer class with essential properties like CPU, RAM, and storage, making it straightforward to manage a computer's specifications. The specs method of the computer class allows us to display these attributes neatly. To facilitate flexible configurations, we introduce the computer builder class. This builder initializes default empty values for CPU, RAM, and storage, enabling a clear strategy for setting these properties. Each setter method, setCPU, setRAM, and setStorage, returns the builder instance itself, allowing for method chaining. This design approach enhances readability and usability by enabling a fluid and intuitive interface for crafting a computer's configuration. Upon completion of the desired specifications, we call the build method to create a new instance of the computer class, encapsulating the final configuration. The usage example illustrates how a user can seamlessly construct a computer with a specific setup using the computer builder, and then retrieve and display its specifications, demonstrating the pattern's practical advantages in managing complex object construction. In this section, we explore the prototype pattern, which simplifies the process of creating new objects by duplicating an existing one. Here, we define a car class that encapsulates the attributes of a car, such as its make, model, and year. The constructor initializes these properties when a new instance is created. The standout feature of this class is the clone method, which utilizes the prototype pattern by allowing us to create a new car instance that mirrors the attributes of an existing object, referred to as original car. This method enhances efficiency, especially in scenarios where instantiating a new object from scratch can be resource-intensive. When we create an instance of car using specific attributes and then call the clone method on it, we generate a new instance, cloned car, that retains the same properties as the original car. This approach minimizes the repetition of code and aids in scenarios where variations of a base object are needed, making object management more straightforward and performance-friendly. As we wrap up our deep dive into the creational patterns in JavaScript, it's important to remember that these patterns are not just theoretical constructs, but essential strategies that enhance our coding practices. They encourage us to think about object creation logically, promoting code that's easier to read, maintain, and extend. Creational patterns like the factory method, abstract factory, singleton, builder, and prototype each bring unique advantages, helping us model our products in a way that suits our application's evolving needs. As you continue to develop your applications, be sure to keep these patterns in your toolkit. They can make a world of difference in how you approach object creation and management. Stay tuned, as we will further explore practical applications of these creational patterns in real-world scenarios and related design patterns in our upcoming lessons. Happy coding! In today's lesson, we will explore the practical implementation of design patterns in JavaScript. Our focus will be on enhancing the functionality of a car manager object using the command pattern, allowing us to execute various operations more flexibly. So far, we learned about various creational design patterns in JavaScript, including the factory method, abstract factory, singleton, builder, and prototype patterns. These patterns provide flexible and efficient ways to create objects, manage dependencies, and maintain variations without exposing the complexities of instantiation. We explored how they enhance code maintainability and readability while promoting a structured approach to object creation. As we continue, we will delve into practical applications of these patterns in real-world scenarios. In this segment, we focus on the implementation of the car and car manager classes, essential components for managing car operations. The car class represents individual car objects, encapsulating their attributes, such as id and model. This simple structure sets the stage for handling car data effectively. The ComManager class serves as a collection manager for car instances, allowing for various operations. Through its methods, we can add cars to the collection, remove them by their ID, and update existing cars with new model names. The addCar method appends a car to the internal array and logs a confirmation message, ensuring that users know a car has been added. The removeCar method efficiently filters the car collection based on the provided ID, utilizing JavaScript's array methods to ensure swift deletions while notifying users of the action taken. Finally, the updateCar method first searches for a car by ID and updates its model if found, providing feedback in case the car doesn't exist. Together, these methods facilitate robust management of vehicle records, laying a strong foundation for implementing more advanced features, such as the command pattern, which we will explore next. In this section, we implement the command pattern to manage correlated operations through encapsulated command classes. We define a base class called command with a unified interface for executing actions. This approach creates an abstraction layer between the request and the execution of the action, promoting decoupled code design. We then introduce three specific command classes: addCarCommand, removeCarCommand, and updateCarCommand. Each of these classes is initialized with a reference to the ComManager and the relevant data needed for the action. For instance, addCarCommand takes both the ComManager instance and the car object to be added, allowing it to call the addCar method when the execute method is triggered. Similarly, removeCarCommand requires the car ID to remove, while updateCarCommand needs the car ID and the new model to update the car's information. This organization enables us to manage commands independently, allowing us to easily pass and execute them without requiring ComManager to know the specifics of each operation. With this encapsulation, the command pattern enhances flexibility in executing various car actions while maintaining clean and manageable code architecture. Now that we've established our command classes, we need a mechanism to manage and execute them efficiently. The command invoker serves this purpose by acting as a queue manager for commands. It maintains an array of commands that have been set, allowing us to execute them in the order they were added. When we instantiate the command invoker, it initializes an empty array to hold the commands. The setCommand method enables us to add new commands to this array, ensuring they can be executed later. This allows us to stage multiple operations without triggering them immediately. The car functionality lies in the executeCommands method, where all queued commands are iterated over, invoking their execute method. By clearing the command array after execution, we avoid duplicate executions in subsequent calls to the method. This design not only streamlines handling of commands, but also prepares our structure for scalability, enabling us to handle complex workflows and operations effectively, all while keeping our code organized and maintainable. In this section, we bring together all the components we've discussed to illustrate the functionality of our ComManager with the command pattern. We start by creating an instance of the ComManager class, which holds our collection of cars, and an instance of the command invoker, which manages our commands. Next, we instantiate two car objects, the Toyota Corolla and the Honda Civic, which will be managed by the ComManager. We then create command objects that encapsulate the add actions for these cars, using the addCarCommand class to facilitate adding them to the ComManager. By setting these commands in the invoker, we maintain a structured approach to execute multiple commands at once. After adding the cars, we also implement an update operation by creating an updateCarCommand instance, allowing us to change the model of the first car. This demonstrates how our invoker executes a command through a simple interface. Lastly, we illustrate the removal of a car with the removeCarCommand, showcasing the flexibility and decoupling provided by our command pattern implementation, allowing for streamlined command management and potential future enhancements. So, you may be wondering, why would you go to the trouble of setting this up when it may seem more straightforward to call those methods directly? The magic here is in the added flexibility and scalability. Imagine if you want to add features like undo and redo functionality. The command pattern makes this straightforward, since each command knows how to execute itself. This means we can stop previous commands and call their undo methods when necessary. Each command can be enhanced with an undo method to reverse its operation. For example, the add car command could take a car's ID and, before adding it, validate if it exists, enabling easy reversal if needed. Another excellent addition to command patterns is batching commands. Instead of executing each command immediately, you could modify the command invoker to hold commands and only execute them in bulk at a given time, thus optimizing performance for more extensive operations. This can be particularly beneficial in cases where network calls or updates to a database are involved, allowing multiple operations to execute once rather than repeatedly. Moreover, testing and maintaining the code becomes substantially easier since each command encapsulates specific behaviors. You can unit test individual commands independently from the rest of the application, ensuring they work as intended without needing to interact with the entire state of the car manager or other components. In conclusion, design patterns, particularly the command pattern we are highlighting today, offer structure and reusability to the codebase. They promote a clean separation of concerns, allowing each component to focus on its responsibility without entangling with others. As a new developer or even a seasoned programmer, applying the command pattern can lead to cleaner code and better architecture, ultimately resulting in a more maintainable and scalable application. This lesson illustrated how to implement a simple command pattern within a car manager context, but the concepts extend far beyond. Consider other scenarios where you can apply these structures, be it in game development, UI event handling, or any system where actions can be clearly defined and decoupled from their execution. Thank you for joining me today. Keep coding and experimenting with these patterns to find solutions that work best for your projects. MVC is an architectural design pattern that encourages improved application organization through a separation of concerns. This makes it easier to manage complex applications by dividing them into 3 interconnected components: the model, the view, and the controller. Each of these components has its own responsibilities, allowing developers to enhance code modularity and maintainability. So far, we've learned about the practical implementation of design patterns in JavaScript, focusing on the command pattern to enhance the functionality of a car manager object. We covered various creational design patterns, emphasizing their benefits in creating flexible, maintainable code. The lesson detailed how to encapsulate correlated operations using command classes and implement a command invoker to manage these actions dynamically. This approach streamlines the management of commands and prepares the codebase for future extensions like undo-redo functionality and batch processing. Now we will dive deeper into the MVC pattern, understanding its components and how they interact with one another to create powerful web applications. In this section, we illustrate how the model component of the MVC architecture can be implemented in JavaScript through the definition of 2 classes, task and task model. The task class encapsulates the properties of a single task, such as its ID, title, and completion status, and includes a method to toggle its completion state. This design encapsulates the behavior of individual tasks, making the code more manageable. The task model class serves as a collection manager for multiple tasks, holding an array to store them. It features methods for adding new tasks and retrieving the current list of tasks. When a new task is added, it creates a new task instance with a unique ID, ensuring each task can be distinctly identified. This separation of data management into the task model enhances the organization of the application, allowing for clear interactions between the user input and the underlying task data that it represents. By encapsulating all task-related logic here, the task model ensures the application adheres to the principles of maintainability and scalability inherent in the MVC design pattern. The provided code demonstrates the implementation of the view component in our MVC architecture for a task management application. The code begins with a simple HTML structure that includes a division for the task list, a header, and an unordered list where tasks will be displayed. This structure is essential for enabling a clear presentation of the tasks to the user within the browser environment. Next, we define the TaskView class in JavaScript, which has a constructor that initializes the task list by selecting the HTML element with the ID tasks. This allows the class to manipulate the DOM dynamically. The displayTasks method plays a crucial role as it handles the rendering of the tasks. Before displaying the new tasks, it ensures that the existing list is cleared to avoid duplicates. It then iterates over the tasks passed as an argument, creating a list item for each task that includes the task's title and its completion status. By appending these list items to the task list element, we ensure that the displayed tasks accurately reflect the current state of the data from the model, demonstrating the synergy between the view and model components in the MVC framework. The task controller class serves as a crucial intermediary in our MVC architecture, facilitating interaction between the model and the view. Within the constructor, we initialize the model and view, enabling the controller to leverage both components seamlessly. Upon instantiation, the controller immediately calls the displayTasks method on the view, passing in the current list of tasks retrieved from the model. This ensures that the user interface reflects the most up-to-date data right from the start. The main function of the controller is encapsulated within the addTask method, which orchestrates the addition of new tasks. When this method is invoked with a task title, it first communicates with the model to add the new task to its internal data structure. Importantly, after modifying the model, the controller promptly updates the view by invoking displayTasks again. This two-step process not only adds new data, but ensures that the user interface remains synchronized with the underlying data state, illustrating the dynamic interaction facilitated by the MVC pattern. Thus, the task controller effectively manages the flow of data and updates between the model and view, maintaining the application's responsiveness to user actions. In this snippet, we bring our MVC application to life by integrating the controller with user interactions in the DOM. Here, we assign an on-click event handler to a button element identified by the ID addTask. This event listener triggers a function when the button is clicked, demonstrating how user actions can dynamically influence the application's behavior. Within this function, we first read the value from an input field with the ID task input, which allows users to enter a new task title. This is a crucial step in enabling user interaction, as it captures the user's input directly from the web page. Once the task title is fetched, we pass this value to the addTask method of our controller instance, task controller. This interaction embodies the MVC architecture, wherein the view, the button and input, communicates with the controller to manage the application's state. By invoking the controller's method, we ensure that the new task is added to the model, facilitating a clear flow of data and enhancing the application's responsiveness to user-generated events. This setup effectively showcases the core functionality of the MVC pattern in a web application. In this section, we focus on unit testing the task model class to ensure its functionalities work as expected. The testing framework utilized here is Jest, which allows us to create a suite of tests for our model. First, we establish a describe block that groups our tests for the task model. Inside, we initialize a new instance of task model before each test runs with the beforeach method. This setup ensures that each test starts with a fresh model, preventing any state carryover that could affect results. The first test checks if a task can be added successfully by invoking the addTask method, and then verifying that the length of tasks in the model is as expected. The second test further ensures that the task title is accurately stored when a new task is added. By validating these functionalities in isolation, we maintain high code quality and assure ourselves that even as the application evolves, the core functionality of our task model remains intact. This emphasizes the significance of testability within the MVC architecture, allowing for confident, incremental improvements. Another notable point about the MVC pattern is its scalability. As applications grow in complexity, organizing code into models, views, and controllers ensures that we can manage enhancements and updates more effectively. If we need to add new features, we can do so by simply creating new models, views, or controllers without affecting the existing components. For instance, if we want to add a feature to filter completed tasks, we can implement a new view method without altering the existing functionality. Understanding how the MVC pattern promotes separation of concerns will allow developers to structure their applications thoughtfully. Consider how you might face changes or refactoring in the future. With MVC, the development workflow becomes more manageable and your codebase easier to navigate. To wrap up, the MVC design pattern plays a pivotal role in modern application development. It empowers developers by separating functional concerns into 3 distinct layers. The model handles data and business logic, the view manages the user interface, and the controller focuses on handling input and controlling the flow between the model and view. This structure not only improves code organization, but also enhances scalability, testability, and maintainability. In summary, we've explored the significance of the MVC pattern in creating well-structured applications. You learned about the roles and responsibilities of models, views, and controllers, and saw how they interact in a practical example. By implementing MVC in your projects, you can create more robust and manageable applications, making your life as a developer far easier. Understanding the distinctions between MVC, MVP, and MVVM is crucial for any aspiring developer. These 3 architectural patterns help manage complexity in applications by promoting a clear separation of concerns. Today, we'll delve into these patterns, their unique roles, and how they differ, especially focusing on how MVP and MVVM are derivatives of the MVC pattern. So far, we have learned about the MVC architectural pattern, which divides applications into 3 components: model, view, and controller, each with distinct responsibilities. We discussed the implementation of a task management application, outlining how each component interacts to manage data effectively and respond to user input. We highlighted the benefits of this design pattern, including improved code organization, scalability, and testability. Moving forward, we will continue to explore advanced concepts related to MVC and its practical applications. In this session, we'll take a closer look at MVP and MVVM, 2 influential derivatives of MVC, to highlight the unique characteristics and underlying principles. Let's begin with the traditional MVC pattern. The model, as we learned, is responsible for managing the data and business logic of the application. The view presents this data to the user and captures user input, while the controller serves as the intermediary that processes input, updates the model, and refreshes the view accordingly. The interaction is quite straightforward. The controller receives input from the view and updates the model, which in turn notifies the view of changes. In essence, MVC creates a reactive system, where updates in one part of the application trigger changes across others, promoting a cohesive flow. Data equals title equals MVC example. Content equals learning MVC is powerful. Function render $data. Echo h1 data title /h1. Echo p data content /p. Simulating input from the controller. Render $data. In this example, we implement a simple task management system using the MVP architectural pattern, which clearly separates the responsibilities of the model, view, and presenter. The task model class is responsible for managing the application's tasks, providing methods to add a task and retrieve the current list of tasks. This encapsulation of data management makes it easier to modify and maintain the underlying logic without affecting the user interface. The task view class focuses on displaying the tasks and obtaining input from the user. It features a method to print the current list of tasks and another method to prompt the user for a new task. This clear distinction enables us to keep the UI logic separate from the data management. The task presenter bridges the model and view, handling user actions and updating the view accordingly. When a new task is added, the presenter retrieves the input from the view, updates the model, and refreshes the view to reflect the latest changes. This structure promotes easier testing since we can isolate the presenter's logic without involving the view or model, enhancing the overall flexibility and maintainability of the application. In this example of the MVVM architectural pattern, we implement a simple user management application that clearly illustrates the interactions between the model, view, and view model. The user model class is responsible for managing user data, allowing us to add new users and retrieve a list of existing users. This encapsulation of data management is essential, as it separates the application's core logic from presentation concerns. The userViewModel class serves as an intermediary, containing the logic to connect the model with the view. Upon instantiation, it loads user data from the model and defines methods to add users, which subsequently refreshes the user list. This separation of responsibilities enhances maintainability and facilitates testing. The userView class is dedicated to rendering the UI and handling user input. It utilizes the view model to display the user list and respond to actions, such as adding users. When the user inputs a name, the view updates the view model, which updates the model, showcasing the reactive nature of MVVM. This design allows changes to flow seamlessly through the application, improving user experience through real-time updates. At this point, let's evaluate the key differences among MVC, MVP, and MVVM. In MVC, the controller manages user input, while the view and model communicate directly. MVP provides a more distinct separation, where the presenter takes control of all interactions with the view, allowing for better testability. On the other hand, MVVM introduces reactive data binding between the view and view model, making it a great choice for applications with complex user interfaces. The choice among these structures depends heavily on the needs of the application. For instance, MVC might be better suited for simple applications where the complexity of the UI doesn't justify additional abstraction layers. Meanwhile, MVP can simplify unit testing due to its separation between the view and presenter. MVVM shines in environments where real-time updates are critical, allowing for a fluid user experience without extensive manual synchronization. Let's discuss one more important aspect: the context of usage for each pattern. MVC is traditionally found in web applications, particularly those built with frameworks like Ruby on Rails or Django. MVP, on the other hand, is commonly used in desktop and mobile applications, especially where testing the UI logic separately is crucial. MVVM is popularly recognized in environments that heavily rely on data-driven UIs, such as WPF, Xamarin, or any rich client application where data binding capabilities are leveraged. To illustrate this further, consider a scenario where you're building a mobile application for task management. If you choose MVC, you might implement a simple to-do list where changes to the tasks will reflect across views, although it could become unwieldy as you scale. With MVP, you could ensure that your logic is reusable and isolated, perhaps during the testing phase or when building a more complex feature set. Opting for MVVM would allow you to bind the list of tasks reactively, allowing instantaneous updates in the UI whenever tasks are added or completed. In conclusion, each architectural pattern, MVC, MVP, and MVVM, offers unique advantages tailored to specific design needs. Understanding their differences enhances not just your ability to write effective code, but it also enriches your problem-solving toolkit when faced with different challenges in application development. As you become familiar with these patterns, you'll find that each has its niche wherein it shines, ensuring that your applications are both efficient and maintainable. Embracing these concepts will not only make you a better developer, but also empower you to build complex applications with confidence and creativity. Thank you for joining me today as we explored these vital architectural patterns. The modern landscape of software development has evolved rapidly, particularly concerning architectural patterns applied in web applications. Today, we'll delve into the summary of modern MV patterns, discussing how frameworks, such as Backbone and Knockout.js, which were once popular for implementing MVC and MVVM, have fallen out of favor. So far, we learned about 3 essential architectural patterns: MVC, MVP, and MVVM, each distinctively contributing to separating concerns in application development. Now, we will cover how these patterns have evolved, the current trends in MV patterns, and what the future may hold. To understand the summary of modern MV patterns, we should first acknowledge the landscape that has shifted significantly in recent years. The rise of frameworks like React, Angular, and Vue has brought about a revolution in how applications handle data and user interactions. These frameworks often blend concepts from MVC, MVP, and MVVM, leading to hybrid approaches that enhance performance and developer experience. For instance, while React is often hailed as a UI library, it embraces the component-based architecture that encapsulates the view and the controller together, allowing developers to manage state seamlessly. In this snippet, we illustrate the MVC pattern using a simple task management application. We start by defining the task class, which acts as the model. This class encapsulates the task's data, specifically the task name, and provides an initializer method to set this property. Next, we have the task controller, representing the controller of the application, which contains the createTask method. This method creates a new instance of the task model whenever a task is added, effectively managing the business logic. The TaskView class represents the view, responsible for displaying information to the user. It includes a show method that prints the task's name to the console. As we instantiate the task controller and call the createTask method, we generate a new task with the name Learn Modern MV Patterns. This task is then passed to the task view, where the show method is called to output the task's information to the screen. This clear separation of concerns among the model, view, and controller not only promotes organized code, but also simplifies future modifications and enhancements, thus demonstrating the strengths of the MVC architecture in software design. In this section, we delve into a simple implementation of the MVVM pattern using JavaScript to illustrate its practical application. The task model class encapsulates the core data management logic, maintaining an array of tasks. It provides methods to add new tasks with addTask and retrieve the current list of tasks with getTasks. This separation of data logic from presentation allows for a clean architecture. Next, the TaskView model serves as the bridge between the model and the view. It initializes with a reference to a task model instance, allowing it to access task data. In the loadTasks method, the view model retrieves tasks from the model to keep its own tasks array in sync. The addTask method demonstrates a key MVVM concept. When a new task is created, it updates the model and then reloads the task list. This ensures that any view using the view model will always display the latest data, with minimal manual updates. Finally, we create an instance of task model, followed by a TaskView model instance that interacts with the model. When we add a task, it's confirmed with a console log displaying the updated task list, reinforcing the data binding concept central to MVVM. In this React component, we build a simple task management application that uses the useState hook to maintain a list of tasks. The useState hook is crucial as it introduces state management directly within the functional component, simplifying the process of tracking and updating data. Initially, we set up an empty array for tasks, which will update as users add new ones. The addTask function is defined to take a task name as an argument and update the task state by creating a new array that includes all previous tasks plus the new task. This approach ensures that we do not mutate the state directly, adhering to React's best practices for state management. In the rendered output, we display a header for the task list, followed by an unordered list that iterates over the tasks array, dynamically creating list items for each task. Each item is assigned a unique key using the index value for optimal performance. Finally, a button is provided that calls the Add Task function when clicked, illustrating user interaction and showcasing how we can easily update the UI in response to events. This encapsulated structure exemplifies the component-based architecture of React, streamlining UI logic and state management within a single cohesive unit. In this section, we will explore how Vuex manages application state in a Vue.js framework, enabling seamless interaction between components and centralized data management. We start by importing Vue and Vuex, followed by registering Vuex as a plugin in the Vue instance. The creation of the Vuex store involves defining the state, which initially holds an empty array called tasks. This state contains the application's data, with a specific mutation called add task, responsible for appending new tasks to the state. Mutations are synchronous transactions that ensure state changes are predictable and easy to understand. Within the Vue instance, we define a template that features a task list with a title, an unordered list that dynamically displays tasks, an input for creating new tasks, and a button to add those tasks. The computed property tasks allows us to access the tasks state from the Vuex store, ensuring that our component always reflects the latest application state. The add task method commits the new task to the store and resets the input field, demonstrating how Vuex promotes reactive data flow and effective state management within the user interface. As we look to the future, the evolution of MV patterns does not appear to be slowing down. New frameworks continue to emerge with improved efficiencies in handling complex applications. The integration of server-side rendering, static site generation, and progressive web applications within these architectures is also notable. The asynchronous nature of modern web applications demands that frameworks adapt, leading us to concepts like microservices and serverless architectures. For instance, in a microservices setup, we could utilize a front-end framework, like React on the client side, communicating with multiple back-end services in a straightforward manner through REST-TFL APIs or GraphQL. As developers, it is our responsibility to stay abreast of these changes and to understand how these evolving architectural patterns can enhance our applications. Recognizing when to use a particular approach depends on project requirements, team skills, and the goals of the application being developed. In this discussion, we explored the state of modern MV patterns and how they relate to the frameworks gaining traction today. The transition from older frameworks like Backbone and Knockout.js to component-driven solutions highlights the need for flexibility and efficient data management in application development. We hope this overview provides insight into how these patterns can have a powerful influence on your coding practices. In summary, understanding modern MV patterns, including MVC, MVP, and MVVM's evolution, enhances our ability to construct applications effectively. As we adapt to newer frameworks and programming paradigms, the opportunities for innovation expand, allowing us to build complex, maintainable applications. Thank you for joining today's lesson, and happy coding. Asynchronous JavaScript programming allows you to execute long-running tasks in the background while allowing the browser to respond to events and run other code to handle these events. This capability is essential in providing a smooth user experience in web applications, where users expect immediate feedback, even while complex operations are underway. In this lesson, we will delve into the intricacies of asynchronous programming, exploring key concepts such as callbacks, promises, and the modern async await syntax, along with practical examples to illustrate each point. So far, we've learned about the evolution of software architectural patterns in web applications, focusing on MVC, MVP, and MVVM. We've observed a shift from traditional frameworks like Backbone and Knockout.js towards modern frameworks such as React, Angular, and Vue, which integrate these patterns into component-based architectures. This transition emphasizes improved performance, data management, and a clearer separation of concerns in application development. We also highlighted that staying informed about these trends is crucial for creating efficient and maintainable applications. Now, we will cover how asynchronous programming enables these modern architectures to function seamlessly by preventing the blocking of the main thread and enhancing the overall user experience. In this section, we illustrate the stark contrast between synchronous and asynchronous programming through practical examples. The synchronous function demonstrates a typical synchronous execution pattern where the program processes tasks serially. When invoked, it first logs start, then enters a loop simulating a time-consuming task, effectively freezing the browser's main thread until it concludes this operation. Only after the loop is completed does it log end, highlighting synchronous programming's potential to hinder user interactions during lengthy operations. Conversely, the asynchronous function exemplifies how asynchronous programming maintains responsiveness in applications. When executed, it logs start, initiates a fetch request to retrieve data from a specified URL, and instantly logs end. This immediate feedback illustrates that while the fetch operation runs in the background, the main thread is free to respond to other events or execute additional code. The data retrieved from the server is then logged to the console once available. This demonstrates the power of asynchronous functions, showcasing how they enhance user experience by allowing applications to continue processing other tasks seamlessly while waiting for potentially time-consuming operations to complete. In this section, we explore the use of callbacks in asynchronous programming through a practical example. The makeRequest function is designed to fetch data from a given URL and takes a callback function as an argument. Once the fetch request is initiated, it processes the response by converting it to JSON. After that, it calls the provided callback with either the fetched data or an error, depending on the outcome of the request. When invoking makeRequest, we specify a URL and provide an inline callback function to handle the result. Within this callback, we check if an error has occurred. If so, we log the error to the console. Otherwise, we display the retrieved data. This pattern illustrates how callbacks enable us to define actions based on the success or failure of asynchronous operations. However, it's important to note that while callbacks are straightforward, they can lead to complex code structures, particularly when multiple asynchronous calls are nested, commonly referred to as callback hell. This example sets the foundation for understanding more advanced asynchronous patterns as we move forward. In this section, we'll explore how promises enhance our asynchronous JavaScript code for better readability and maintainability. The makeRequest function initiates a new promise, which encapsulates the asynchronous operation of fetching data from the provided URL. When calling the fetch method, the first then block processes the response and converts it to JSON, while the second then fulfills the promise by resolving the data. In case of any errors during this process, the catch method captures and handles them gracefully, rejecting the promise. Next, we see how promises enable chaining, allowing for sequential asynchronous operations without falling into callback hell. By taking the result of the first makeRequest call, we can log the data and then immediately initiate a second request for more information. This clean chaining ensures that each step waits for the previous one to complete before executing, which is crucial in asynchronous programming to maintain order and logic flow. This approach not only simplifies the code, but also enhances readability, making it easier for developers to follow along with the asynchronous workflow. In this example, we define an asynchronous function named fetchPosts to demonstrate the power and simplicity of using async await for handling asynchronous operations in JavaScript. The function is prefixed with the async keyword, indicating that it will perform asynchronous tasks. Inside the function, we employ a try-catch block to manage errors effectively. This structure is fundamental for maintaining clean and readable code when dealing with potential issues arising from asynchronous requests. Within the try block, we use the await keyword to pause the execution of the function until the promise is returned by makeRequest resolve. This means that the function will wait for the data from the specified API endpoints before proceeding. We start by fetching the first post and logging it to the console, followed by the second post in a similar manner. If any error occurs during these operations, the control moves to the catch block, where we log the error to the console, ensuring that the application can handle failures gracefully. Overall, this approach enhances code readability, reduces nesting, and makes asynchronous handling more intuitive, aligning with the principles of modern JavaScript development. In this part of the lesson, we leverage the benefits of async await along with promise-all to execute multiple asynchronous operations simultaneously. The function, fetch multiple posts, is defined as an asynchronous function, which allows us to use the await keyword to pause execution until the promises from the requests are resolved. Inside the function, we initiate two fetch requests to retrieve posts from an external API, specifically targeting two different post endpoints. By wrapping these requests in promise-all, we enable both operations to run concurrently rather than sequentially, which significantly enhances performance. This means that while the first post is being fetched, the application will not wait idly but will start fetching the second post right away. Once both promises resolve, the function destructures the results into post 1 and post 2, which are then logged to the console. Such an approach not only optimizes the time taken to fetch data, but also illustrates the power and efficiency of modern JavaScript async patterns. In addition, error handling is elegantly managed within a try-catch block, ensuring that any issues encountered during the fetch operations are caught and logged, promoting robustness in our code. As we conclude, it's crucial to acknowledge error handling in asynchronous programming. With callbacks, errors need to be handled manually in each callback. With promises, the catch method can catch errors in any of the chained calls. However, when using async await, you can encapsulate the logic in try-catch blocks, as shown previously, providing a clean approach to managing exceptions. To summarize, asynchronous programming in JavaScript empowers developers to write non-blocking code, improving the user experience by allowing applications to respond to events swiftly. The evolution from callbacks to promises, and finally to async await, illustrates the continuous enhancement of the language as it adapts to the needs of modern applications. As you incorporate these techniques into your work, you will find opportunities to create more efficient, responsive, and maintainable web applications. In future lessons, we'll explore more advanced topics related to asynchronous programming, like cancellation of requests and the implementation of concurrency patterns. Promises are a more modern approach to handling asynchronous operations in JavaScript. A promise is an object that represents the result of an asynchronous operation, simplifying async code management and enhancing readability. In this lesson, we will delve into promise patterns and usage, unpacking how they work, their advantages, and how to effectively implement them in your code. So far, we learned about asynchronous programming in JavaScript, which enables non-blocking execution of long-running tasks, ensuring that web applications remain responsive to user interactions. We explored key concepts such as callbacks, promises, and the async await syntax, highlighting their roles in simplifying asynchronous code management and improving readability. The evolution from callbacks to promises and async await illustrates the advancements in handling asynchronous tasks, offering cleaner error management and parallel execution capabilities. Now, we will cover promise patterns and their practical usage in real-world applications. In this section, we illustrate the cost structure of promises in JavaScript through a practical example. We begin by creating a new promise using the promise constructor, which takes a function with two parameters, resolve and reject. Inside this function, we simulate a condition for success using a Boolean variable named success. If success is true, we call resolve with a success message, transitioning the promise to the fulfilled state. Conversely, if success were false, we would call reject with an error message, marking the promise as rejected. following the promise creation, we handle the outcomes using the then and catch methods. The then method receives a callback that logs the result to the console, ensuring it executes only when the promise is fulfilled. The catch method acts as an error handler, capturing any rejection to log the error. This structure not only illustrates the promise's state transitions, but also emphasizes the importance of clear error management in asynchronous operations, making the code more robust and easier to maintain. In this example, we demonstrate how to effectively use promise chaining to handle asynchronous operations sequentially. The fetchUser function simulates fetching user data by returning a promise that resolves to a user object after a 1-second delay. This user object contains the user's ID and username, represented in a structured format. Once the user data is retrieved, the then method receives the user object and allows us to log it to the console for verification. The next step leverages the user ID to fetch related posts using the fetchPosts function, which also returns a promise and simulates a delay before resolving with an array of post objects. This structure keeps our code clean and avoids the confusion often associated with nested callbacks. Finally, the subsequent then method processes the posts, also logging them to the console. We've also included a catch method at the end to gracefully handle any errors that may arise during the promise execution, highlighting the effective error management that promises provide. This approach exemplifies the power of promise chaining in managing multiple asynchronous tasks systematically. In this example, we define a function named fetchData that simulates a failed data retrieval operation. The function returns a new promise which intentionally rejects after a 1-second delay, indicating that data could not be found. This simulation showcases error handling in promises. When fetchData is called, we chain two methods, then and catch. The then method is designed to handle the fulfilled case, logging the retrieved data, but in this scenario, it won't execute since the promise is rejected. Instead, control moves to the catch method, which captures the error and logs it gracefully to the console. This demonstrates how promises allow us to centralize error management, avoiding the chaos of scattered error checks as seen in callback patterns. Additionally, the finally method is included, which runs regardless of whether the promise was fulfilled or rejected, making it an ideal place for executing cleanup code or displaying a final message about the fetch attempt's completion. This structure not only enhances readability, but also effectively manages both success and error scenarios in asynchronous JavaScript operations. In this section, we will delve into the usage of the promiseAll method to handle multiple asynchronous operations efficiently. The fetchDataFromAPI function simulates an API call, creating a promise that resolves with a string indicating the data source after a random delay. This randomness mimics the varying response times you might experience when fetching data from real APIs. Next, we have an array of URLs that we intend to fetch data from. By mapping this array to the fetchDataFromAPI function, we generate an array of promises. The promiseAll method is then utilized to execute all of these promises in parallel, meaning the operations are initiated simultaneously rather than sequentially. This greatly enhances efficiency, especially when making multiple API requests. Once all promises are resolved, the results are logged to the console. However, should any promise encounter an error and reject, the catch block will handle the error gracefully, logging it to the console. This structured approach to handling multiple asynchronous operations not only saves time, but also improves code readability and maintainability, essential features in any JavaScript application. In this section, we leverage PromiseRace to handle asynchronous operations efficiently. The fetchDataWithTimeout function initiates a promise that fetches data from a given API URL while also setting up a timeout feature. This function uses setTimeout to reject the promise if the data fetch exceeds a specified duration. When the fetch operation completes first, it clears the timeout to prevent unnecessary rejection and resolves with the fetched data. We then create a different promise, timeout promise, which will automatically reject after 2 seconds if not fulfilled. The crux of our implementation comes with promise race, where we pass an array containing both fetch data with timeout and timeout promise. This ensures that the first promise to settle, whether it's the data fetch or the timeout, determines the outcome. If the data is received in time, we handle it in the then method. Otherwise, any errors will be caught by the catch method. This approach is particularly useful in scenarios demanding quick responses, giving users a fallback when network conditions are suboptimal. It illustrates how to manage multiple asynchronous tasks effectively while safeguarding against delays. In this section, we'll explore a practical utility function that simplifies API requests using the fetch API. The API request function returns a promise, allowing users to manage asynchronous behavior effectively while handling errors uniformly. When the function is invoked with a URL, it initiates a fetch call. Inside this promise, we check the response status using responseOK, which indicates whether the request was successful. If the response is not OK, it rejects the promise with an error message that includes the HTTP status code. This structured error handling ensures that any issues with the request are caught early. Upon receiving a valid response, the function extracts the JSON data and resolves the promise with this data. The promise chaining allows users to attach then and catch methods to handle the resolved data or any potential errors more cleanly. In the example provided, calling API request with a sample URL demonstrates logging the return posts or any errors encountered, showcasing the ease of managing asynchronous requests through this utility function. This approach not only streamlines code, but also enhances maintainability when dealing with multiple API interactions. As we wrap up our lesson, remember that promises are a core feature of modern JavaScript and essential for asynchronous operations. They help keep your code clean and structured, avoiding the infamous callback hell while empowering you to execute tasks efficiently, manage errors effectively, and simplify complex asynchronous workflows. By utilizing promise patterns like chaining, promise-all, and promise race, you'll have the tools necessary to handle any asynchronous task your application throws at you. As you move forward, keep practicing with promises, and soon they will become second nature in your coding toolkit. In upcoming lessons, we will explore more advanced topics like request cancellation and concurrency patterns, equipping you with even more techniques for mastering asynchronous JavaScript. Stay tuned. Asynchronous programming can often begin to feel like a maze, especially when dealing with long-running tasks. But don't worry, we're here to navigate this maze together. Today, we'll explore advanced asynchronous patterns and error handling in JavaScript, enhancing your toolkit for tackling complex scenarios. So far, we've learned about promises as a modern solution for handling asynchronous operations in JavaScript, covering topics like promise states, chaining, error management, and methods like promise-all and promise race. Now, we will take a deeper dive into more advanced techniques that will provide you with a robust approach to asynchronous JavaScript. In this section, we will explore the fetch with concurrency function, a vital tool for managing multiple asynchronous requests effectively. This function takes two parameters: a limit that specifies the maximum number of concurrent requests allowed, and an array of URLs to fetch data from. The function initializes two essential components: an empty results array to store the responses, and a set called executing to keep track of currently executing promises. As we iterate through the URLs, each fetch request is transformed into a promise that resolves to the JSON data. This promise is then added to the results array, while also being tracked in the set of executing promises. To ensure we don't exceed the defined concurrency limit, the code checks the size of the executing set after adding a new promise. If the limit is reached, the function awaits the completion of any promise in the set by utilizing promise race, which resolves as soon as one of the promises settles. Finally, by using promise-all, the function ensures that it waits for and returns the results of all fetch requests once they have all completed, providing a robust solution for handling concurrent data fetching while preventing performance issues. In this section, we implement a robust error handling mechanism for our asynchronous operations through the use of an error boundary. The fetchDataWithBoundary function demonstrates how to wrap a fetch call in a try-catch block, which is essential for catching potential errors during the fetch process. If the response is unsuccessful, we throw an error that includes the HTTP status code, providing clear insight into what went wrong. Any errors encountered within this function are logged to the console, allowing for easier debugging without disrupting the overall application flow. Next, we have the fetchMultipleData function, which leverages our error boundary by mapping over an array of URLs and invoking fetchDataWithBoundary for each one. This mapping creates an array of promises that allows us to utilize PromiseAll, ensuring that all valid responses are handled. Even if one of the fetch calls fails, the other successful responses are still returned, which exemplifies how error boundaries centralize error management, leading to a more resilient application. This design effectively enhances user experience by preventing complete failures when some requests do not succeed. In this segment, we explore how to implement cancellation for ongoing asynchronous operations using the *bot controller API. We begin by creating an instance of the bot controller, which manages the request's cancellation, and we capture its signal for use in our fetch request. When making a fetch call, we pass the signal in the request options. This allows us to control the fetch operation effectively. If we need to cancel the request, we simply invoke controllerBot. This action will trigger an abort error, which we can catch within the try-catch block of our asynchronous function. This error handling is crucial, as it allows us to differentiate between an aborted request and other potential errors that may arise during the fetch operation. By logging an appropriate message for both scenarios, we enhance resource management by avoiding unnecessary processing when a request is canceled. This approach not only optimizes performance, but also significantly improves user experience by ensuring that requests that are no longer needed do not consume system resources. In this section, we explore the implementation of the throttling technique, which optimizes the execution of a function by limiting how frequently it can be called. The core of the throttle function is centered around maintaining timestamps to control the invocation of a specified function, ensuring it executes at defined intervals. When the throttled function is executed, it checks the current time against the last time it was run. If the time elapsed meets or exceeds the set limit, it calls the function, allowing for the desired action, such as logging an event, to be performed. If the function is invoked again before the time limit is reached, it does not run immediately. Instead, the implementation utilizes a timeout to schedule the function's execution again after the remaining time. This approach conserves resources by preventing multiple rapid executions, especially beneficial for high-frequency events like scrolling. For instance, attaching the throttled function to a scroll event, listener, means that the console will only log a message at most once per second, regardless of how frequently the scroll event fires. This not only reduces performance overhead, but also enhances user experience by maintaining application responsiveness. In this section, we will focus on implementing a debounce function, which is crucial for optimizing user input handling. The debounce function takes two parameters: the function to be executed and the wait time before it can be called again. Inside the function, a timeout variable is initialized to track the delay. When the user invokes the debounced function, the first action is to clear any existing timeout, ensuring that previous calls do not trigger the function prematurely. The next step involves setting a new timeout that will execute the past function only after the specified wait period has elapsed since the last call. This approach effectively groups multiple calls into a single execution, allowing the function to fire only after the user has stopped typing for the specified time duration. In practical use, we apply this debounce function to an input field, listening for the input event. By wrapping the console log inside the debounced function, we prevent unnecessary fetch requests for every keystroke, instead triggering the data fetch once the user has paused their typing for 500 milliseconds. This greatly enhances performance and user experience in applications involving real-time data fetching based on user input. In this section, we focus on implementing an *** error handling strategy using a centralized logging system. The error logger class serves as the backbone for our error management, containing a static method called logError that takes an error object as an argument. This method is designed to log error information, allowing for better visibility into issues that may arise during application execution. While currently it logs errors to the console, you can extend it to send error data to a dedicated logging server for further analysis. The fetchData function illustrates how to integrate this logging mechanism during asynchronous operations. When attempting to fetch data from a specified URL, it employs a try-catch block to handle potential errors gracefully. If an error occurs, say due to an unsuccessful HTTP response, it throws a new error with a descriptive message. Instead of just logging this error to the console, it utilizes the error logger to log the error centrally, promoting better application stability. This structured approach ensures that developers can efficiently track and resolve issues, ultimately maintaining the health of their applications. As we finish our exploration of advanced asynchronous patterns, remember that these techniques not only enhance your coding practices, but significantly improve user experience and application performance. Effective control of promises, thoughtful error management, cancellation, throttling, debouncing, and centralized error logging are vital concepts to wield as you tackle complex programming challenges. With these advanced patterns in your toolkit, you'll be able to write cleaner, more efficient, and user-friendly code that stands resilient against the myriad challenges you might encounter in asynchronous programming. The world of JavaScript is dynamic, and by mastering these techniques, you've built a strong foundation to handle even the most intricate asynchronous flows with confidence. Thank you for joining this journey, and keep experimenting and implementing these advanced patterns as you grow your skills in asynchronous JavaScript. In the world of scalable JavaScript, modularity is everything. It allows developers to create applications with distinct pieces of functionality stored in modules, ensuring a cleaner and more maintainable codebase. In the rectangle.js file, we define two essential functions, calculateArea and calculatePerimeter. These functions are designed to perform specific calculations for rectangles, thereby adhering to the modular programming principle of focusing on a single concern. The calculateArea function takes two parameters, length and width, and returns the product of these values, which represents the area of the rectangle. Similarly, calculatePerimeter computes the perimeter by summing twice the length and twice the width, reflecting the formula for the perimeter of a rectangle. An important aspect of these functions is the use of the export keyword. By exporting these functions, we make them accessible to other modules that may need to utilize rectangle calculations. This promotes code reusability and encapsulation, as the functionalities are neatly packaged into one module. As you develop applications, organizing your code into modules like Rectangle.js allows for better maintainability, clearer structure, and easier collaboration among team members, all of which are fundamental to creating scalable JavaScript applications. In our project, we've created a dedicated module for circles, which helps maintain a clean and organized codebase. The circle.js file begins by defining a constant pi, ensuring easy access to the value of pi for any calculations involving circles. We then export two functions, calculateArea and calculateCircumference. The calculateArea function takes the radius as an argument and returns the area calculated using the formula pi2, while calculateCircumference computes the circumference using the formula 2pi. This encapsulation not only separates circle-specific logic, but also enhances code reusability and readability. Next, we move to app.js, where we import the necessary functions from both the rectangle and circle modules. By using descriptive aliases, like rectangleArea for rectangle area calculations, we mitigate potential naming conflicts and maintain clarity within our imports. The main application logic demonstrates how to invoke these functions, leading to clear console outputs for the area and perimeter of rectangles, as well as the area and circumference of circles. This approach showcases the power of modular design in JavaScript, making our application extensible and easier to manage. In this segment, we enhance our rectangle module by incorporating input validation. The validate dimensions function is defined to ensure that both the length and width provided are positive numbers. If either value fails the check, an error is thrown with a clear message, guiding users toward correct usage. This function is then utilized within both calculate area and calculate perimeter functions before performing their respective calculations. By invoking validate dimensions, we encapsulate error handling, making the module more robust and user-friendly. This approach highlights how modular JavaScript not only organizes code, but also improves its reliability through encapsulation. By ensuring inputs are validated, we prevent unexpected behaviors that could arise from invalid data during calculations. This clear separation of concerns within the module allows it to evolve independently, as changes to validation logic won't affect the rest of the application. Overall, this makes our rectangle module more maintainable while enhancing its functionality through improved error management. In our modular JavaScript application, we introduced a utility module, utils.js, to handle shared constants and validation functionalities. This module exports the constant pi, representing the value of pi, and a function called validatePositiveNumber, which checks whether a given value is greater than 0. This validation is crucial for ensuring that our application only processes valid inputs, preventing errors down the line. Next, we updated our existing rectangle.js module to leverage the validation from utils.js. By importing the validatePositiveNumber function, we maintain cleaner code that adheres to the dry principle, avoiding code duplication. In the validate dimensions function, we now call validatePositiveNumber for both the length and width parameters. This enhancement not only reduces the risk of errors by centralizing validation logic, but also makes future updates easier. Should we need to change the validation criteria, we only need to update utils.js. Consequently, our area and perimeter calculations in rectangle.js become more robust, ensuring that invalid dimensions trigger appropriate errors without cluttering the logic in our shape modules. In this section, we'll explore a simple Webpack configuration file designed to optimize our modular JavaScript application for production. The configuration begins by requiring the path module, which is essential for resolving directory and file paths. The entry property specifies the starting point of the application, pointing to app.js, which is where our modular code initializes. Next, the output object defines how and where the bundled code will be emitted. In this case, Webpack will create a file named bundle.js within the dist directory. This output process combines all the imported modules into a single file, simplifying file management for distribution. The configuration also includes a module property that defines how different types of files are transformed before bundling. Here, we set up rules for processing JavaScript files. Specifically, we use Babel Loader, which allows us to transpile modern JavaScript into a version that can run in older browsers. By using the options provided to Babel, we ensure broader compatibility across various environments, making our application more accessible to users. This setup illustrates how Webpack effectively handles dependencies while optimizing our code for a seamless user experience. In this section, we will explore the sphere.js module, which was created to calculate the volume of a sphere. The module begins by importing two essential elements from the utils.js file, the constant pi, which represents the mathematical constant pi, and the validatePositiveNumber function, which ensures that any given number is positive. This validation step is crucial because the radius of a sphere cannot be negative or 0. Performing calculations with invalid input would lead to meaningless results. Next, we define the calculateVolume function, which takes a single parameter, radius, The first line of this function calls validate positive number, passing the radius to check its validity. If the input is valid, the function proceeds to calculate the volume of the sphere using the formula \frac_4_3 times /pi times r3 where r is the radius. This mathematical operation utilizes the mathpow method to compute \r3. By encapsulating the volume calculation and validation within its own module, we maintain modularity, making it easy to test and integrate this functionality into a larger application without disrupting existing code. In conclusion, modular JavaScript represents a significant leap toward building scalable, maintainable applications. By breaking our code into distinct modules, we improve code clarity, collaboration, and encapsulation. Whether you're working on a small project or a large-scale application, adopting modular practices will serve you well. Moreover, the ability to leverage modern tools for module bundling and dependency management further solidifies modular JavaScript as a best practice in the development community. So today, we've walked through the benefits of modular JavaScript, learned how to use modules and manage dependencies, and while I haven't made too many jokes, I hope my enthusiasm shines through. The world of JavaScript is constantly evolving, but mastering modularity gives you a strong foundation to build upon. Happy coding, and see you in the next lesson. Both AMD and CommonJS are valid module formats with different end goals. Understanding these standards is crucial for building scalable and maintainable applications in JavaScript. Today, we'll dive deep into these two popular module systems and explore how they differ, their use cases, and how to implement them in practical scenarios. So far, we learned about the significance of modular JavaScript in creating scalable and maintainable applications through the use of distinct modules. We explored how breaking code into smaller pieces enhances organization, encapsulation, and collaboration among developers. The lesson covered the creation and interconnection of various modules while demonstrating practical examples, such as modules for calculating areas and volumes of different shapes. Finally, we examined the advantages of utilizing modern build tools to optimize and streamline the application development process. Now, we will cover AMD and CommonJS, two module formats that shape JavaScript development today. In our example, we begin by defining a simple arithmetic module named math.js. This module encapsulates two fundamental operations, addition and subtraction. Within the module, the add function takes two parameters, a and b, and returns their sum. Similarly, the subtract function performs the opposite operation, returning the difference of the two inputs. By leveraging module exports, we make both functions accessible to other JavaScript files, thereby promoting modularity and code reuse. Next, we move to app.js, where we focus on utilizing our math.js module. We begin by importing the math module with the require function, which synchronously loads the module and its exported functions. Upon loading, we can directly call massadd to calculate the sum of 5 and 3, and mathsubtract to find the difference between 9 and 4. The results are then logged to the console, providing a clear output of each operation. This straightforward approach highlights the effectiveness of CommonJS in managing dependencies and reusing code, particularly suited for server-side applications where synchronous loading enhances organization and maintainability. In the AMD module system, we define our math.js module using the define function, which facilitates the declaration of module dependencies in an asynchronous manner. Here, we pass an empty array as the first argument since our module does not depend on any other modules. The second argument is a factory function that contains our arithmetic operations. Inside this function, we define two functions: add, which takes two parameters and returns their sum, and subtract, which calculates the difference between two numbers. Finally, we return an object that exposes these two functions, allowing them to be accessed by any module that requires math.js. Moving to app.js, we use the require function to load the math module. Notice that this loading is asynchronous, meaning the main application continues to run while it waits for math.js to load. Once loaded, the callback function is executed, where we call the add function with 5 and 3 to compute the sum, and subtract with 9 and 4 to find the difference. Finally, we log these results to the console, showcasing how easy it is to utilize the arithmetic functions defined in our module. This non-blocking approach exemplifies AMD's suitability for client-side JavaScript development. Now, let's delve deeper into some nuances between the two module systems. A significant difference comes from the way they handle dependencies. In CommonJS, the dependencies are loaded synchronously, meaning each require statement halts execution until the module is loaded. This straightforward approach is beneficial for server-side implementations where time spent loading modules is less impactful. On the other hand, AMD allows declaring dependencies at the time of defining the module. This leads to a more complex, but ultimately more flexible, approach for managing dependencies, especially in apps where performance and loading speed are prime concerns. Furthermore, because AMD works asynchronously, it can load modules in parallel, thus potentially decreasing overall load time for your application. Let's begin with the CommonJS example that demonstrates how to implement a user management module. In this code, we utilize the require function to import the session management module. This synchronous loading means the application will wait for the session module to load entirely before proceeding. The getUser function is defined to check if a user is authenticated by calling sessionIsAuthenticated. If the user is authenticated, the logic for retrieving the user's details would execute. This setup allows for clear dependencies and simple function exports, emphasizing how CommonJS facilitates server-side JavaScript development with its straightforward module structure, making it ideal for environments like Node.js. Next, we transition to the AMD example, which showcases a similar user management module without the blocking behavior of CommonJS. Here, we declare a dependency on the session module using the define function. This function not only specifies the dependencies, but also provides a factory function that produces the module's functionality. When user.js calls sessionIsAuthenticated, it does so in an environment where both modules may be loaded concurrently, enhancing performance. This non-blocking approach is particularly beneficial for web applications, allowing other elements of the page to render while waiting for the required modules. When considering which module system to use, it's essential to understand the context of your project. If you're developing a Node.js application or a server-side environment, CommonJS is often the go-to choice due to its straightforward nature and synchronous loading. However, for web applications where performance and user experience are key, AMD's asynchronous nature can provide significant advantages. Additionally, there's also a shift in the JavaScript world with the introduction of ES modules, which build on these principles and effectively unify module syntax in JavaScript, a project that is still ongoing. It's worth noting that many modern build tools and frameworks now support ES modules while maintaining compatibility with both CommonJS and AMD, allowing developers to write in their preferred format. Let's examine how we implement user authentication in both the CommonJS and AMD module formats. In the CommonJS implementation, we have two modules, login.js and auth.js. The login.js module requires the auth module and defines a login function that accepts a username and password. It checks if the user is authenticated by calling the authAuthenticated method and logs a welcome message if successful or indicates invalid credentials otherwise. The use of module exports here makes the login function available for use in other JavaScript files, maintaining modularity and separation of concerns. On the other hand, the AMD version also utilizes these two modules, but is designed for asynchronous loading. In this case, login.js defines its dependencies, specifically the auth module, using the define function. The authentication logic remains similar, However, the asynchronous nature means that the application can continue functioning without blocking while the auth module is being loaded. This allows for a more responsive user experience, especially beneficial when integrating APIs or handling multiple resource requests concurrently, illustrating the strength of the AMD format in handling modern web application requirements. Before we wrap up, it's important to mention a few tools and libraries that can assist with module loading. In the world of AMD, Require.js is a popular library that helps manage module dependencies and loading effectively. Some development environments even employ bundlers and task runners that utilize these standards to enhance the build process. Webpack and Parcel, for instance, can transpile CommonJS and AMD modules while enabling you to use ES modules, allowing you to write in the latest JavaScript syntax and still enjoy the benefits of modular standards. In conclusion, both CommonJS and AMD are critical components of the JavaScript ecosystem, each designed to meet specific needs and improve how we manage code structure. While CommonJS suits server-side development with its simplicity, AMD paves the way for progressive web development where performance is vital. Understanding these modules and when to use them enhances your ability as a developer and equips you to tackle a wide array of JavaScript projects efficiently. Keep exploring and experimenting with these modules, and you will find them invaluable in your coding journey. That's a wrap on understanding AMD and CommonJS standards. With these foundational principles and code examples in your toolkit, you're now better equipped to choose the right module format for your next JavaScript application. Happy coding! We are diving into a powerful concept today, UMD, or Universal Module Definition, which enables us to write modules that work across different environments. This is crucial for modern development as it enhances compatibility and makes our code more resilient. So far, we learned about the importance of module systems in JavaScript, specifically focusing on CommonJS and AMD formats. CommonJS is geared towards server-side development with synchronous loading, while AMD supports asynchronous loading suitable for client-side applications. We explored examples of creating and using modules for arithmetic operations in both formats and discussed the implications of each approach on application performance. Understanding these differences will help you choose the appropriate module system based on your project's needs. Now, we will cover UMD and explore how it combines the best of both worlds, allowing us to create modules that can seamlessly run in various environments. In this code snippet, we implement the Universal Module Definition, UMD pattern, which allows our module to work seamlessly across different JavaScript environments like AMD, Node, JS, and traditional browsers. The outer function immediately invoked takes two parameters: root, representing the global scope, like window in a browser, and factory, where we define our COM module logic. The conditional checks within the function ascertain which environment the code is executing in. If it detects AMD through the presence of define, it calls define to register the module. For Node, JS, it verifies if xbots is an object and uses module xbots to expose the module. Finally, for browsers not using module loaders, it assigns the output of the factory function to a property on the global object, establishing myModule. Inside the factory function, we define two essential operations: add and subtract. By returning an object that contains these functions, we create a simple, reusable math module. This structure exemplifies the flexibility and adaptability that UMD provides, ensuring that our arithmetic operations can be used across various environments without additional hassle. In this section, we expand our utility module to include additional arithmetic operations while adhering to the UMD pattern. The code begins by wrapping the entire module in an immediately invoked function expression, IIFE, that takes in root and factory as parameters. This structure enables the module to adapt seamlessly to different environments. Inside, we define four core functions: add, subtract, multiply, and divide. The addition and subtraction functions work as expected, while the multiply function utilizes the multiplication operator to return the product of two numbers. A critical feature is the error handling implemented in the divide function, which throws an error if an attempt is made to divide by 0, thereby preventing runtime crashes that could disrupt application flow. Finally, the module returns an object containing references to all four functions, allowing them to be easily accessed and utilized. By adopting the UMD pattern, the MathUtils library is now versatile enough for integration across various platforms, showcasing its compatibility whether used in AMD loaders, Node.js, or standard browser environments. In this section, we'll see how to utilize the MathUtils module across different environments using the UMD pattern. In a Node.js application, we start by requiring the MathUtils module, which enables us to access its arithmetic functions. For instance, we can call the add function to sum two numbers, easily logging the result to the console. This approach showcases how UMD allows for a seamless integration of the module within a server-side environment without requiring any additional configuration. Moving to a browser scenario with Require.js, we can set up our script with a datamain attribute pointing to main.js, which initializes our module loading. Within main.js, we use the require function to asynchronously load the MathUtils module. After successfully importing it, we can leverage the subtract function to calculate the difference between two numbers, and again, output this result with a console log. This highlights the UMD pattern's true strength, its flexibility across environments, allowing the same code to operate without modifications, ensuring a smooth developer experience across various platforms. In this section, we implement a charting module that leverages the UMD-defined MathUtils for calculating averages. The UMD pattern ensures that this module can be utilized seamlessly across different environments, such as Node.js or in the browser. We begin by creating an immediately invoked function expression that takes root and factory as parameters. This structure allows us to check the environment. If it's an AMD environment, we define the module using define to specify its dependency on MathUtils. If we detect a CommonJS context, we require MathUtils within our factory. Finally, for a browser global setup, we attach the chart module to the global object, enabling easy access. Inside the factory function, we define a calculateAverage function that takes an array of numbers as input. By utilizing the add method from MathUtils, we calculate the sum of the numbers. Subsequently, we divide the total by the length of the input array to arrive at the average. This modular and flexible approach ensures that developers can use the chart module consistently across various platforms, showcasing the power and versatility of UMD in modern JavaScript development. We should also consider one important aspect of UMD: how it can simplify library distribution. When you package a library defined in UMD, you essentially create a single file that can be distributed on platforms like NPM or GitHub, allowing developers to include it easily in their projects without worrying about compatibility issues. Many developers are working within a module bundler setup, such as Webpack. For these individuals, UMD can be instrumental when you want to create libraries that can be used in multiple contexts while still allowing the bundler to handle module resolution efficiently. Say you are creating a specialized library for image processing that utilizes asynchronous methods. You could design this library using UMD pretty easily. The developer using this library can do so with CSS or JavaScript and would achieve the same result without deep configurations. One might wonder, is there a downside to using UMD? Like any solution, it comes down to trade-offs. While it offers enormous flexibility, it introduces extra code for the necessary checks for environment types. In small projects, this might be overkill, and a simpler module format could suffice. However, for larger libraries or those intended for public use, the benefits of UMD far outweigh the downsides. In a rapidly evolving landscape, where tools and environments continuously shift, The upfront cost of added code becomes insignificant compared to long-term maintainability and adaptability. As we've seen, UMD is crucial for developers aiming to write robust JavaScript libraries. By enabling compatibility across environments, it offers a best-of-both-worlds solution that alleviates the friction often experienced during module loading and library distribution. Understanding how to implement and leverage UMD allows you to be more flexible and efficient while writing code that meets the demands of modern development environments. To wrap up, today, we explored universal module definition and its pivotal role in achieving cross-environment compatibility in JavaScript. We began by discussing its structure based on CommonJS and AMD patterns and how these styles can serve very different scenarios. With practical examples, we structured our code in a way that highlights the flexibility and robustness of UMD, allowing your modules to be easily employed in multiple contexts without tangled dependencies. In your journey as a developer, embracing UMD will not only enhance your understanding of modular JavaScript, but also empower you to create libraries that others can use freely, irrespective of the environment. So, as you build your projects moving forward, consider the advantages of weaving UMD into your toolkit. Happy coding! In this example, we demonstrate the concept of namespacing using an immediately invoked function expression, IIFE. The IIFE creates an encapsulated scope for our application logic, ensuring that variables and functions remain private and do not pollute the global namespace. Within the IIFE, we define a function called doSomething, which simply logs a message to the console. This encapsulation is crucial for avoiding conflicts with other scripts that may run in the same environment. The IIFE then returns an object that exposes the doSomething function, allowing it to be accessed publicly while keeping its internal logic hidden. To invoke the method, we call myappDoSomething, which outputs the message to the console. By using a single object as a namespace, we minimize the risk of naming collisions with external code, ensuring that our functions are organized and maintainable. This pattern is particularly effective for larger applications, where encapsulating functionality within an object can lead to clearer, more structured code. Overall, this approach lays a solid foundation for building scalable JavaScript applications. In this section, we introduce the concept of prefix namespacing as a way to manage global variables and avoid naming conflicts in a JavaScript application. By adopting a prefix that reflects the application's name, such as myapp, we create a clear and organized structure for our variables. For instance, we define two properties, myappPropertyA and myappPropertyB, both of which can hold various data structures or values specific to our application. Additionally, we create a function named myappMyFunction, which encapsulates functionality associated with our application. This function includes a simple console log statement, demonstrating how we can create reusable and easily identifiable methods. The use of such prefixes not only helps in distinguishing application-specific variables from potential global keyword conflicts, but also contributes to improved readability of the code. However, as an application scales, it's essential to ensure that the prefixes remain unique to prevent clutter in the global namespace, thus maintaining the overall organization and manageability of the codebase. In this segment, we will delve into using object literal notation to create a neatly organized namespace in JavaScript. Here, we define myapp as an object that encapsulates properties and methods in a single entity. This approach not only maintains a clean structure, but also simplifies management by grouping related functionalities. The myapp object features two properties, property A and property B, both initialized as empty objects. This allows for further expansion and organization of related data or functions later on. Additionally, myapp includes a method, myFunction, defined within the object for easy access. When this function is invoked, it outputs a clear message to the console, demonstrating how methods can be neatly encapsulated. Moreover, the flexibility of this structure enables scalability. You can dynamically add more layers of organization as your application grows. For instance, additional properties like models, views, and controllers can be introduced to handle various aspects of your application, ensuring that your codebase remains organized and maintainable as you expand functionality. This showcases the power of object literal notation in crafting efficient namespaces in JavaScript. In this example, we demonstrate the concept of nested namespacing in JavaScript, a technique that helps organize code into a hierarchy of namespaces. The code begins by checking if the MyApp object already exists to avoid overwriting it, allowing for a smooth integration into larger applications. Following that, we create utilities as a subnamespace within MyApp, which houses related functionality. By ensuring that utilities and subsequent nested namespaces like math are initialized only if they do not already exist, we maintain a clean structure and prevent potential conflicts with other code. The add method is defined within the math namespace, highlighting how grouping related functions enhances clarity. This method takes two parameters, a and b, and returns their sum. Finally, we demonstrate the functionality of this setup by logging the result of my app, utilities, math, add 5.3, which outputs 8. This structured approach not only aids in code organization, but also ensures that as applications grow, the related functions and properties remain accessible and logically grouped. One powerful technique for managing namespaces in JavaScript is the use of immediately invoked function expressions, IIFEs. In the provided code, we define a function that runs as soon as it is defined. This function creates a new scope, encapsulating certain variables and methods within it. Here, a private variable containing the string I am private and a private method function are declared, but they cannot be accessed directly from the outside. Instead, the IIFE returns an object that exposes a public method. This public method serves as an interface, allowing external code to trigger the private method indirectly. When public method is called, it executes private method, which then prints the value of private variable. This structure safeguards the private variables from outside interference and potential naming conflicts, while still allowing controlled access to functionality through the exposed public method. By using IIFEs, developers can effectively encapsulate functionality and create modular code that is easier to maintain and less prone to collisions with other scripts. In this example, we implement the concept of namespace injection using an immediately invoked function expression, IIFE. We begin by ensuring that MyApp is defined as an empty object if it doesn't already exist, allowing us to create a namespace called utils, where our utility functions will reside. Within the IIFE, we declare a variable named value and create two methods, getValue and setValue. These methods interact with the value variable, allowing us to retrieve its value and update it, respectively. The significance of using this inside the IIFE is that we leverage the apply method to set the context to my app, utils. This means the methods, getValue and setValue, are directly accessible as properties of my app, utils, promoting modularity and preventing global namespace pollution. This pattern not only encapsulates our functionalities within the my app, utils, namespace, but it also makes it easier to manage and apply behaviors across different parts of our application. Overall, namespace injection enhances maintainability, reduces the risk of naming collisions, and improves code readability. In the following code, we define a function called extendObjects that automates the process of merging objects, particularly useful for creating nested namespaces. This function takes two parameters, destination and source. It iterates over the properties of the source object. For each property, it checks if the property is an object itself. If it is, it initializes that property in the destination object if it doesn't already exist and recursively calls extendObjects to handle the nested merging. If the property is not an object, it directly assigns the value from source to destination. After defining this function, we create an empty object named myAppNamespace, which serves as a container for our application's organized structure. We then call the extendObjects function, passing myAppNamespace, along with a new object that includes a nested utils object and a math object containing an add method. This method can take two arguments and returns their sum, showcasing how easily we can group related functionalities while ensuring our code remains structured and clear. Ultimately, this code helps build a well-organized application namespace with logically grouped methods, enhancing maintainability and readability. Using namespacing techniques should be seen as laying the foundation for large-scale applications. By ensuring that your code is modular, preventing naming conflicts, and improving readability through structured organization, you're setting yourself and your team up for ongoing success in code maintainability and collaborative development. To summarize, we explored various techniques for implementing namespacing in JavaScript, including single global variables, prefix namespacing, object literal notation, nested namespacing, immediately invoked function expressions, and namespace injection. Each method offers unique advantages depending on the complexity of your application. By adopting these strategies, you can prevent conflicts, enable better organization, and ultimately create more maintainable and scalable JavaScript applications. In our next discussion, we'll dive into practical examples and further explore how to refactor existing code using these namespacing patterns. Stay tuned. In this example, we illustrate the use of a single global variable for namespacing in JavaScript with the creation of a library object called myLibrary. This object functionally encapsulates related methods, ensuring that they are organized within a single namespace, which helps prevent naming conflicts. Within myLibrary, we define two methods, greet and farewell. The greet method takes a name as an argument and returns a greeting string that incorporates that name, while the farewell method offers a similar function by providing a goodbye message. After defining the object, we showcase its utility by invoking the greet method with Alice and the farewell method with Bob. The results demonstrate the encapsulation provided by using the myLibrary object, as it allows for an organized structure where the methods can coexist without interfering with functions or variables defined elsewhere in the global scope. While this approach is effective for smaller applications, it's crucial to recognize that relying too heavily on a single global object may lead to longer, less readable names as the application grows. In this section, we see an implementation of prefix namespacing, a technique that helps organize functions and variables to avoid naming conflicts. Here, each function related to the mylib namespace is prefixed with mylib, ensuring that these identifiers are uniquely associated with our library. The first function, mylibGreet, takes a name as an argument and returns a greeting string that addresses the user personally. This allows the function to customize the output based on the passed parameter, demonstrating how we can use dynamic content in our code. Similarly, the second function, mylibFarewell, serves to bid farewell to the user and returns a parting message, again personalized by the name provided. By utilizing this prefixing approach, we keep our library functions distinct, which minimizes the chances of conflicts as we add more features. However, while prefix namespacing is straightforward, it can lead to a cluttered global namespace if not managed carefully, especially in larger applications where the number of prefixed variables can grow rapidly. This serves as a good stepping stone before exploring more complex namespacing strategies in the next sections of our tutorial. In this segment, we implement the concept of object literal notation to create our own library of functions. Here, we define a constant named myLibrary, which serves as a namespace containing related methods. Within this object, we have two methods, greet and farewell. The greet function takes a single parameter, name, and utilizes template literals to return a friendly greeting. Similarly, the farewell function also accepts a name and returns a goodbye message. By organizing these functions within the myLibrary object, we maintain a clean structure that enhances code readability and simplifies the management of related functionalities. Furthermore, this approach minimizes the risk of naming conflicts in the global scope, as all methods are encapsulated within myLibrary. In practice, We can invoke these functions easily, as demonstrated in the subsequent console log statements that show how to greet Eve and bid farewell to Frank. This method of using object literal notation allows for effortless expansion. You can add more methods as needed without cluttering the global namespace. In this segment, we delve into implementing nested namespacing to further organize our code within the MyLibrary structure. Here, we define a main object called MyLibrary, which serves as the primary namespace, encapsulating all related functionalities. Inside this object, we create a utilities property that houses two categorized objects, math and string. The math object includes two methods, add and subtract, to perform basic arithmetic operations. This categorization allows developers to group functions according to their purpose, which simplifies code navigation and maintenance. Similarly, the string object contains methods for manipulating string values, such as toUpperCase and toLowerCase, which change the case of given text inputs. By structuring our utility functions in this manner, we not only enhance the organization of our codebase, but also mitigate the risk of naming conflicts that can arise in larger applications. The clear hierarchy created by nested namespacing enables easier access to specific utilities, ensuring that developers can quickly locate the functionality they need without sifting through a flat structure. In this section, we introduce immediately invoked function expressions, or IIFEs, which are valuable for creating a local scope in JavaScript. The code demonstrates how to encapsulate variables and methods, shielding them from the global namespace, which helps prevent conflicts in larger applications. Here, we define MyLibrary using an IIFE, which executes immediately and returns an object. This object provides a public interface with two methods, public greet and call private method. The public greet method takes a name parameter and returns a greeting, emphasizing the use of template literals for string interpolation. On the other hand, call private method invokes private method, which logs the value of private variable. This structure effectively keeps private variable and private method hidden from the outside world, thus maintaining privacy and integrity within the code. By using IIFEs, we facilitate better organization and encapsulation, allowing developers to collaborate on complex applications without risking naming conflicts or exposing unnecessary code to the global scope. In the following code snippet, we explore the concept of namespace injection, which allows us to extend existing namespaces while maintaining encapsulation. Here, we first check if the MyLibrary variable already exists. If it doesn't, we initialize it as an empty object. This pattern ensures we don't overwrite any previous definitions of MyLibrary and safely create a new namespace if necessary. Next, we define a utils property on the MyLibrary object, which will serve as a designated area for utility functions within the library. The core of our namespace injection is an immediately invoked function expression, IIFE, that creates a private scope. Inside this IIFE, we declare a variable secret value that is not accessible from outside. Instead, we expose a method, getSecretValue, which allows controlled access to this private variable. By applying this function directly to MyLibrary, utils, using apply, we effectively inject the method into this namespace, enhancing the overall structure and readability of our code while preventing global scope pollution. When we call getSecretValue, it retrieves the hidden value, demonstrating the effectiveness of this pattern in maintaining organization and encapsulation. To wrap this up, we've covered 6 essential namespacing patterns that can dramatically improve the organization of your JavaScript code. Single global variables, prefix namespacing, object literal notation, nested namespacing, immediately invoked function expressions, and namespace injection. Each pattern serves to mitigate the risk of naming conflicts and helps maintain your code's structure as it scales. Adopting these patterns allows developers to write cleaner, more maintainable code that is easier to navigate. Separating logic into well-defined namespaces prevents cluttering the global scope with unnecessary variables and functions. Using these strategies, you can create a robust application that holds up well over time and adapts to changing requirements. So, as you embark on your coding journey, remember these namespacing patterns. They might just be your best friends in avoiding the chaos that comes with larger JavaScript applications. Thanks for joining me on this deep dive into namespacing patterns in JavaScript and happy coding. In today's lesson, we will delve into advanced namespacing techniques in JavaScript that can significantly enhance your coding practice, especially when working on extensive applications. We'll explore some advanced patterns and utilities that I have found invaluable when working on more extensive applications, some of which have required a rethink of traditional approaches to application namespacing. So far, we learned about namespacing patterns in JavaScript, which are crucial for organizing code and preventing naming conflicts. We explored techniques like single global variables, prefix namespacing, object literal notation, nested namespacing, IIFEs, and namespace injection. Each of these patterns helps to maintain a clean code structure and improve readability, especially in larger applications. Ultimately, adopting these strategies contributes to writing maintainable and scalable JavaScript code. Now, we will talk about even more sophisticated ways to implement namespacing. In this example, we focus on the module pattern, a powerful technique for encapsulating code in JavaScript. The user module wraps its functionality in an immediately invoked function expression, IIFE, ensuring that the internal variables remain private and protected from the global scope. Inside the module, we define private data, which securely holds the username and password. The getData function serves as a private accessor to private data, safeguarding sensitive information. Instead of exposing this function, we return a public interface with getUsername and isAuthenticated. These methods utilize getData to access user information while keeping the underlying data structure hidden. This provides a clear separation between private and public access, promoting better data encapsulation. The getUsername method allows us to retrieve the username, while the isAuthenticated method checks if the user is logged in based on the presence of a username. This approach not only organizes the code, but also enhances security and maintainability, as changes to the internal state won't affect how the public interface operates. In our exploration of the revealing module pattern, we define a module that encapsulates user-related data and functionality. This pattern enhances accessibility by explicitly returning constants for the methods we want to expose, namely getUsername and isAuthenticated. Inside the module, we have a private variable named privateData, which contains sensitive information like the username and password. Instead of directly exposing this data, we leverage a private function, getData, to access it securely while maintaining encapsulation. The getUsername function retrieves just the username from private data, ensuring that sensitive information remains protected. Similarly, the isAuthenticated function checks whether a username exists, providing a simple way to assess user authentication status. By returning the function references as properties of an object, we create a clear interface for users of the module. This approach not only promotes cleaner code, but also makes it easier to read and maintain, aligning perfectly with our goal of creating scalable applications. The use of the revealing module pattern is particularly beneficial as we handle more extensive code bases, ensuring that we keep access controlled and organized. In this segment, we'll explore how to create and utilize ES6 modules for better code organization and modularity. The user.js file demonstrates how you can encapsulate user-related functionalities by declaring a private object containing sensitive credentials, such as the username and password. This private data stays hidden from other modules, promoting security and encapsulation. The two exported functions, getUsername and isAuthenticated, serve as public API points. The getUsername function retrieves the username from the private data, while isAuthenticated checks if the username is present, returning a Boolean indicating authentication status. This structure allows for concise access to user information without exposing the underlying data directly. In the main.js file, we illustrate how to import these exports from user, JS, enabling us to use the functions seamlessly. The console logs demonstrate calling these functions to display the username and check authentication status. This modular approach not only enhances clarity, but leverages tools like Webpack or Rollup for optimized module handling, providing a cleaner and more maintainable codebase in your JavaScript applications. In this section, we delve into the concept of named and default exports in ES6 modules, which are crucial for effectively managing modular code. Here, we define several utility functions that perform basic arithmetic operations. Addition and subtraction are exported as named exports, making it easy to import them individually as needed. This allows developers to utilize these functions without loading unnecessary code, fostering efficiency. Moreover, we create a default export for the multiplication function. The default export signifies the primary functionality of the module, providing a clear focal point for those using it. When we import from this module in another script, we can easily access both named and default exports in a single import statement. This dual approach enhances clarity in our codebase, ensuring it remains organized while enabling the reuse of multiple utility functions. Understanding the distinction between named and default exports not only improves the architecture of your modules, but also enhances maintainability and scalability in larger applications. This structured approach allows for a coherent coding style that teams can adopt, significantly improving collaboration and reducing potential conflicts as projects grow. In this section, we will explore how to define and utilize modules using Require.js, a powerful tool for managing dependencies in JavaScript applications. First, we define a module named user that encapsulates private data, specifically a username and password. This module employs a closure to maintain the confidentiality of the private data object, exposing only the getUsername method. By returning an object that reveals the getUsername function, we create a clean and intentional interface for interacting with the module, safeguarding sensitive information, while allowing controlled access to certain functionalities. Next, we move on to importing this module in another file, main.js, using Require.js. The require function takes the dependency, user, as an argument and executes a callback function once the module is loaded. Within this callback, we can access the getUsername method of the imported user module to log the username to the console. This example illustrates not only how to structure your modules for better encapsulation, but also demonstrates the advantages of asynchronous loading, which optimizes application performance by loading only the required modules. In this segment, we will explore the implementation of a mixin to enhance class functionality without relying on an intricate inheritance structure. We begin by defining the auth mixin, which contains methods for user authentication and logout, encapsulating common behaviors that can be shared across different user classes. Next, we create two distinct user classes, admin user and regular user. Each class has its constructor to initialize the username. To imbue these classes with the functionalities outlined in the mixin, we utilize object_assign. This method assigns the properties and methods from auth mixin directly to the prototypes of our user classes. As a result, when we instantiate admin user and regular user, they inherit the capabilities defined in the mixin without being tightly coupled to a single inheritance hierarchy. Consequently, when we call the authenticate method on an instance of admin user, it accesses the auth mixin functionality, demonstrating how mixins facilitate code reuse while promoting cleaner, more maintainable code structures. In this section, we're focusing on the practical implementation of namespaces in JavaScript to manage potential naming conflicts between different libraries. Here, we define two separate library objects, library A and library B, each containing an initialize method. By encapsulating the functionalities of these libraries into distinct objects, we effectively create separate namespaces. This prevents any possibility of function name collisions, as both libraries have their own independent versions of initialize. When we call library A initialize, it triggers the function specific to library A, logging a message that confirms its initialization. Similarly, invoking library B initialize calls the corresponding function from library B, demonstrating that both library methods operate without interference. This organizational approach not only enhances the maintainability of your code, but also promotes robustness, particularly in larger applications where multiple libraries might be integrated. By adopting such namespacing techniques, you establish a clean structure that minimizes conflicts and makes your application easier to navigate for yourself and other developers working collaboratively. These advanced namespacing techniques we've discussed today, from module patterns to ES6 modules, dependency management, and mixins, greatly enhance code clarity and maintainability. Keep in mind that naming collisions can introduce bugs that are often tough to track down. By effectively implementing these techniques, not only will your code be more structured, but it will also become easier to read for other developers. As you approach more complex applications, consider the practices we outlined today. This foundational knowledge will empower you to manage larger code bases confidently and ensure smooth collaboration with teammates. Always remember, clean code is happy code, so let's make it shine. Happy coding. React, also referred to as React.js, is an open-source JavaScript library created by Facebook for building user interfaces, or UI components. With its emphasis on efficiency and flexibility, React has become a go-to solution for developers looking to create interactive web applications. So far, we learned about advanced namespacing techniques in JavaScript, emphasizing the importance of organizing code and preventing naming conflicts. We covered various patterns, including module patterns, ES6 modules, and dependency management. Additionally, we discussed mixins and the significance of using namespaces to integrate third-party code without clashes. These strategies contribute to writing maintainable, clear, and scalable JavaScript code. Now, we will talk about the fundamental principles of React and how to get started with this powerful library. To understand React, it's crucial to grasp its core concept, components. Components are the building blocks of any React application. They encapsulate logic and UI rendering combined into one reusable unit. A component can be simple, like a button, or complex, like an entire form. The beauty of React lies in its declarative nature, which simplifies the process of creating interactive user interfaces by allowing developers to describe what the UI should look like based on the current state. This excitement about creating something new continues to drive the React community forward. In this snippet, we define a functional component called greeting, which is responsible for displaying a personalized greeting message. The component accepts a single argument, props, which is an object containing properties passed from a parent component. Inside the function, we utilize JSX, a syntax extension for JavaScript that allows us to write HTML-like code within our JavaScript files to create an H1 HTML element. This element incorporates curly braces to embed the value of props name, enabling dynamic content rendering based on the name prop provided by the parent. To see this component in action, we render it using React.render, targeting an HTML element identified by the id root. This setup not only demonstrates the clarity and simplicity that functional components offer, but also highlights how props facilitate the flow of data within the application. This combination of features makes React components both reusable and maintainable, key principles in building efficient user interfaces. In this code snippet, we are utilizing JSX to render our greeting component within a React application. First, we begin by importing the necessary libraries, React and React.dom. The greeting component is defined as a function that accepts props, allowing it to receive properties passed to it, specifically a name. Inside the function, JSX is used to create an H1 HTML element that displays a greeting message incorporating the name prop. Following the component definition, we utilize React.render to mount the greeting component onto an HTML element with the id of root. This process connects our React component to the web page, enabling it to be displayed in the browser. When this code executes, it dynamically generates a greeting saying, "Hello, Alice" on the screen. This illustrates how React components encapsulate UI logic and properties together, making building interactive user interfaces streamlined and efficient. Additionally, the way we can simply change the name prop to greet someone else highlights the reusability and flexibility of components in React applications. In this section, we'll explore how to implement state in a React component using the useState hook, allowing for dynamic user interactions. The code begins by importing React and the useState and React DOM modules, establishing the necessary foundation for our component. Inside the counter function, we define a state variable called count and initialize it to 0 using the useState hook. This setup provides our component with a piece of state that we can manipulate. The component returns a simple UI consisting of a paragraph that displays the current value of count and a button. When the button is clicked, it invokes the setCount function, which increments the value of count by 1. This action triggers React to re-render the component, ensuring that the displayed count updates accordingly. This mechanism exemplifies React's powerful ability to synchronize the UI with state changes, creating a smooth and engaging experience for users. Overall, the counter component succinctly demonstrates state management in functional components. In this example, we delve into the concept of props in React, showcasing how they facilitate communication between components. The parent component serves as the container that renders two child component instances, each receiving a unique name prop, Alice and Bob. This demonstrates the ability to pass data from a parent to child components, reinforcing the idea of component composition and reusability. Within the child component, we access the passed prop via the props object and dynamically incorporate it into the output using JSX. This immutability of props from the child's perspective is crucial as it enforces a unidirectional data flow, making the application state easier to predict and manage. When the parent component is rendered, it invokes the child component for each name provided, displaying personalized greetings. By utilizing props effectively, you can create more modular and maintainable code, allowing components to remain focused on their specific responsibilities while still enabling dynamic interactions that enrich the user experience in your applications. In this example, we create a simple React component called nameForm that demonstrates how to handle user input efficiently. The component utilizes the useState hook to define a state variable name, initialized to an empty string. This state will hold the value entered by the user in the input field. The handleChange function is defined to update the name state each time the input field changes. This function captures the current value of the input field from the event object and assigns it to the name variable using the setName function provided by the useState hook. The component returns a form that includes an input element and a paragraph that displays the current user input. The input element's value is bound to the name state, ensuring that any changes in the input are immediately reflected in both the input field and the paragraph. This real-time two-way binding creates an interactive user experience, highlighting the power of React in managing state and rendering UI based on that state. Overall, this approach encourages developers to build dynamic forms that respond instantly to user interactions. In this section, we introduce the useEffect hook, a powerful tool for managing side effects in functional components. Here, we create a simple timer component that tracks elapsed seconds. The component begins by defining a state variable, seconds, initialized to 0 using the useState hook. To implement the timer functionality, we utilize the useEffect hook. Inside the effect, an interval is set up to increment the seconds state every second. This is achieved by calling setSeconds with a function that takes the previous state and adds 1. It's important to note that we return a cleanup function, which clears the interval when the component unmounts. This step is crucial, as it helps prevent potential memory leaks by ensuring that intervals aren't left running when the component is no longer in the DOM. Finally, the component returns a simple message displaying the number of seconds elapsed. The design elegantly encapsulates the logic for tracking time while demonstrating the effective application of hooks in React, making it easier to manage side effects in a cleaner, more declarative way. In this section, we will explore how to implement routing in a React application using the React Router library. First, we import React along with essential components from React Router DOM, specifically browser router, route, and link. Within our main component, app, we set up a router that will enable us to define different routes for navigating our application. Using an unordered list, we create a navigation menu with two links, one directed to the home path and the other to the about path. The link component is crucial here as it enables client-side navigation without a full-page reload, preserving the single-page application experience. We define two functional components, home and about, which are simply returning headings. These components are then linked to specific paths through the route component. The exact keyword used in the home route ensures that it will only render when the URL matches exactly, preventing unintended matches with other routes. This routing setup not only streamlines navigation, but also enhances the user experience by enabling quick transitions between different sections of the app without disrupting the entire page. As we wrap up our introduction to React, it's essential to recognize that the library has evolved over the years, embracing new features and enhancements, such as React hooks, that allow developers to write cleaner and more efficient code. Its robust ecosystem includes tools like Redux for state management, allowing for even greater control over application state. Understanding the core principles and components of React is your first step in creating modern web applications that are not only functional, but also enjoyable to work with. With its vibrant community and expansive resources, diving deeper into React will serve any aspiring web developer exceptionally well. You now have the foundational knowledge to start building your own React applications. So, roll up your sleeves, grab your code editor, and start experimenting with what you've learned today. The world of component-based architecture awaits you, and remember, every remarkable application starts with a single line of code. Happy coding! In today's video, we're diving deep into the world of design patterns. These are reusable solutions to commonly occurring problems in software design. Understanding design patterns is crucial as they streamline the development process, promote code reuse, and enhance maintainability. So far, we've covered foundational principles of React, including components, JSX, state management with the useState hook, and how props work. Now, we will explore various design patterns that can elevate your React applications and improve your overall software architecture. In this code snippet, we implement the singleton design pattern through a database class that ensures only one instance of the database connection exists throughout the application. The constructor of the class first checks if an instance already exists, which is stored in a static property called database_instance. If an instance is present, it returns that instance, effectively preventing the creation of multiple connections. If no instance exists, it establishes the connection by calling the connectToDatabase method, where the actual logic for connecting to the database would go, represented here by a console log statement indicating a successful connection. This design is particularly advantageous because it manages resources efficiently. Only a single database connection is maintained. Consequently, when we create two instances of database, represented by DB1 and DB2, both point to the same underlying database connection. This is validated through the comparison console, log db1 == db2, which returns true, confirming our implementation's effectiveness. Overall, this pattern leads to cleaner architecture and helps ensure that your application manages resources in a controlled manner. In this section, we'll explore how the adapter pattern enables compatibility between different interfaces. The first part of our code defines a simple user class that represents a user with a name property. However, in this case, we also have a third-party user class that retrieves user data from an external source, returning it in a different format than our application expects. To bridge this gap, we introduce the useAdapter class. The adapter serves as a middleman that takes an instance of third-party user, and adapts its output to fit our application's needs. Specifically, the getName method in the useAdapter class accesses the incompatible getUserData method from third-party user, extracting the full name property, which is then returned in a format that our application recognizes. Finally, in the usage section, we create an instance of third-party user and pass it to our useAdapter. When we call the getName method on the adapter, it effectively retrieves the expected name format, demonstrating how the adapter pattern not only resolves interface incompatibilities, but also enhances code flexibility. In this section, we'll explore the implementation of the observer pattern through a simple JavaScript example that demonstrates its core functionality. We begin with the subject class, which acts as the central component managing a list of observers. In the constructor, we initialize an empty array to hold the observer instances. The subscribe method allows observers to register themselves with the subject, while the unsubscribe method provides a way to remove observers when they are no longer interested in updates. This ensures that the list of observers remains current and relevant. When a change occurs, the notify method is triggered, sending updates to all registered observers. It iterates through the observers array and calls the update method on each observer, passing the new data. This automatic notification process exemplifies the one-to-many relationship inherent in the observer pattern. The observer class defines what happens when an update is received, in this case logging the new data to the console. Finally, we see how to utilize these classes in practice by creating an instance of subject, registering 2 observers, and notifying them with a message. This setup effectively illustrates the decoupled interaction between components, crucial for large applications. Having discussed these important design patterns, let's look at how they can integrate into our React applications. Design patterns not only provide templates for specific problems, but also establish conventions for communication and organization within our codebase. They enhance our ability to maintain and evolve the application as requirements change over time. Consider using the singleton pattern in a React app service layer. For example, you might have a single service responsible for fetching data from an API. Implementing the singleton pattern for this service class ensures that all components using it share the same instance. This promotes efficient resource usage and makes testing more manageable since you can mock that instance when writing unit tests. On the other hand, the adapter pattern can be particularly useful when working with third-party modules. Suppose you are using an API that returns user data in a format that doesn't align with your current application architecture. By creating an adapter, you can shape the data as per your needs without altering the API responses. This approach makes your application modular and easier to maintain. And for our observer pattern, integrating it with state management solutions like Redux can make state changes predictable and trackable. Using Redux with its observer-like nature allows your components to automatically re-render based on state changes, creating a reactive UI. Want to know what's better? It simplifies debugging since you can easily track how data changes over time and how it affects user interfaces. Now that we've wrapped our minds around various design patterns, it's crucial to understand how they can help you not just write code, but craft applications that are robust, maintainable, and scalable. The patterns discussed today lay the groundwork for creating solid architectures in your future development endeavors. Remember, the key to mastering design patterns is practice. As you work on different projects, try implementing these patterns where relevant. Soon enough, recognizing opportunities to leverage design patterns will become second nature, guiding you to write cleaner and more efficient code. So, get ready to experiment with these patterns and let your creativity flow as you design your applications. I hope this video has shed light on the importance of design patterns and inspired you to integrate them into your workflow. Happy coding, and until next time, keep building amazing things. The PRPL pattern focuses on 4 primary performance considerations that are critical for enhancing the efficiency of web applications. Understanding and implementing these optimization techniques can significantly impact your app's load times and overall performance. In this lesson, we'll delve into advanced performance optimization techniques that can elevate your applications by focusing on the PRPL pattern: push, render, pre-cache, and lazy load. So far, we learned about design patterns, which are reusable solutions to common software design problems that enhance maintainability and streamline development. We covered key types of design patterns: creational, structural, and behavioral, with examples like the singleton, adapter, and observer patterns. These patterns offer best practices to improve architecture and facilitate integration in React applications. Understanding and implementing these patterns can lead to crafting robust and scalable applications. In this section, we explore how to implement dynamic imports with React to enhance our application's performance using the PRPL pattern. The code begins by importing the necessary components from React, specifically React and Suspense. Here, React Lazy is employed for the dynamic import of the lazy component, enabling us to load it only when required. This optimization prevents unnecessary blocking of the initial rendering. Within the app component, we structure our JSX to display a welcoming message: "Welcome to my app." Encapsulated within a suspense component, we utilize a fallback UI div loading div, which provides users with feedback that the lazy component is loading. This is vital for maintaining a seamless user experience. The dynamic loading mechanism allows users to interact with the app right away without waiting for the entire component tree to render, thus significantly enhancing perceived performance. By implementing this asynchronous loading strategy, we align with the PRPL principles, ensuring that critical resources are pushed to the client immediately while less critical ones load in the background. In this section, we will explore how to optimize rendering in React using the use memo and use callback hooks. The code consists of two main components: expensive computation and app. The expensive computation component takes a numeric prop, num, and uses a function, compute, to perform an expensive calculation, summing up all integers from 0 to the given number. To avoid recalculating this value every time the component renders, we use the useMemo hook. This hook memoizes the result of the compute function, recalculating the value only when the num prop changes. This optimization significantly improves performance, particularly when dealing with extensive computations. On the other hand, the app component manages an input field for users to enter a number. It uses the useState hook to handle the state of this input. The handleChange function updates the state, but to ensure that the function reference remains stable across renders, we wrap it in the useCallback hook. This way, we prevent unnecessary re-renders of the expensive computation component, optimizing the rendering process further. Overall, these hooks contribute to a more efficient and responsive user experience in React applications. The following code demonstrates how to register a service worker in a React application, an essential step for enabling features like pre-caching. This snippet first checks if the browser supports service workers, ensuring compatibility. It then sets up an event listener that triggers when the Windows load event occurs. Within this listener, the Navigator Service Worker Register method is called, pointing to the service worker file, /serviceworker.js. If the registration is successful, a confirmation message is logged to the console with the scope of the registered service worker. In case of an error, it catches the exception and logs the failure message. This setup allows your application to use service workers, paving the way for enhanced performance optimizations such as caching and offline capabilities. Moving to the next segment of code, we define the service worker's behavior during its installation phase. Here, we set a constant for the cache name and outline the URLs to cache, which includes essential files like the main HTML page and asset style sheets. An event listener for the install event is added, using the cachesopen method to create or access the specified cache. The assets are pre-cached, meaning they'll be stored locally upon installation. This caching strategy significantly improves load times for users by serving previously cached assets on subsequent visits, ensuring a smoother user experience. In this section, we will dive into the implementation of lazy loading images using React's Intersection Observer API. The lazy load image component starts by utilizing the useRef hook to keep a reference to the image element, which allows us to monitor its position in the viewport. We then introduce a state variable, isIntersecting, initialized to false, which will toggle to true when the image is about to enter the viewport. The intersection observer is created to watch for when the image element intersects with the viewport. Inside the observer's callback function, we check if the entry is intersecting condition is met. If it is, we update the state to trigger the image loading by setting isIntersecting to true and stop observing the current element to avoid additional checks. The useEffect hook ensures that we observe the image reference when the component mounts and disconnects when it unmounts, preventing potential memory leaks. In the return JSX, we render a placeholder, loading image, message until the image is ready to be displayed. This approach significantly enhances the initial loading performance, especially in image-heavy applications, by fetching images only when they are about to be viewed. In summary, the PRPL pattern, encompassing push, render, precache, and lazy load, provides a comprehensive framework for enhancing your web application's performance. By pushing crucial resources quickly, rendering them efficiently, precaching for subsequent visits, and lazy loading non-critical resources, we achieve a smoother and more responsive user experience. Implementing these advanced performance optimization techniques in your applications will not only delight users, but can also lead to improved engagement and retention. The realm of performance optimization is intricate, but with the tools and techniques we've discussed today, you are well equipped to make impactful enhancements to your applications. As you continue to develop and experiment, remember the PRPL pattern and how its principles can elevate your web apps to new heights. Happy coding, and don't forget to optimize for speed. The world of web development is constantly evolving, and one of the most significant advancements we've seen in recent years is the shift toward rendering patterns that optimize how web applications respond to user interactions. Today, we'll dive into the complexities of rendering patterns, specifically focusing on client-side rendering, which plays a crucial role in the development of modern interactive applications. So far, we learned about the PRPL pattern, which includes push, render, precache, and lazy load optimization techniques essential for enhancing web application performance. We also discussed the importance of design patterns in software development, covering key types such as creational, structural, and behavioral patterns that improve maintainability and architecture in React applications. Specific implementations included using dynamic imports for code splitting, React hooks for efficient rendering, and service workers for precaching resources. Lastly, we explored lazy loading techniques to efficiently manage resource consumption and significantly reduce initial loading times. Now we will talk about rendering patterns, their implications, and their implementations in frameworks like React.js. In this example, we implement a simple counter component using React hooks. The useState hook initializes a state variable called count, starting at 0, and provides a function setCount to update its value. The component returns a JSX structure containing a div, which includes a paragraph that dynamically displays the current count and a button that triggers the state update. When the button is clicked, it calls setCount, count plus 1, incrementing the count by 1. This illustrates how React re-renders the component automatically whenever the state changes, allowing the updated count to be reflected in the UI without a full page refresh. This efficiency showcases the power of client-side rendering, as React only updates the parts of the DOM that have changed, in this case, just the paragraph showing the count, rather than reloading or refreshing the entire page. Thus, the counter component serves as a foundational example of state management and event handling in React, emphasizing how interactive UIs can be efficiently built. In this code snippet, we implement code splitting using React's lazy and suspense. The lazy function is used to dynamically import the lazy component, meaning that this component won't be loaded until it's actually needed in the application, specifically when it is rendered for the first time. To enhance user experience during this loading process, we wrap the lazy component within a suspense component. The fallback prop of suspense allows us to display a loading indicator, which in this instance is a simple loading message, while the lazy component is being fetched. This not only allows users to understand that content is being loaded, but also keeps the application interactive. By employing this technique, we effectively reduce the initial bundle size, deferring the loading of components until they are required. This optimized loading strategy helps improve the application's perceived performance, ensuring users have a smoother experience as they navigate through the application. Overall, this approach exemplifies modern rendering patterns that focus on efficiency and user-centered design. In this section, we'll examine how next. JS utilizes static site generation through the getStaticProps function. This function is called at build time, allowing the application to fetch data from an external API, in this case, represented by the URL https://API example com/data. The fetch API is used to retrieve the data, and once the response is received, it's converted into JSON format, making it easier to work with. The key here is that the data fetched is then returned as props, which allows it to be passed directly to the home component when the page is rendered. This means users will receive a fully populated HTML page instantly, improving their experience significantly. Inside the home component, the data is mapped over, dynamically creating a list of items. Each item is rendered within a list, making sure to provide a unique key prop to each list element for optimal rendering performance. This implementation not only enhances the site's SEO by providing fully rendered content, but also boosts initial loading performance, leading to a more engaging user experience. In this snippet, we demonstrate the hydration process in React applications following server-side rendering. The React-DOM-Hydrate function is crucial as it allows React to attach event handlers to the already rendered HTML structure that the server has provided. By using this method instead of React DOM render, we ensure that the existing markup is reused, thus optimizing performance and maintaining the interactivity of our application without needing to reload content unnecessarily. During hydration, React reconciles the server-ended markup with the client-side components, ensuring that the application is fully interactive. If the hydration process is mishandled, discrepancies can arise between the server-generated HTML and the client-side state, which may lead to visual inconsistencies or errors in the user interface. This makes understanding and implementing proper hydration techniques critical for developers aiming to create seamless and fully functional interactive applications. By correctly utilizing React DOM-Hydrate, developers can effectively marry the benefits of server rendering with client-side interactivity, enhancing both performance and user experience. In this section, we'll delve into the implementation of a lazy loading feature using the Intersection Observer API in our React application. The lazy image component starts by importing the necessary hooks from React, specifically useEffect and useState. We maintain a state variable, isVisible, initialized to false, which will control whether the image should be displayed. The useEffect hook is crucial here. It sets up the intersection observer that will watch for the image's visibility within the viewport. When the component mounts, the observer is created and begins observing the DOM element identified by the alt prop, which we set as the id for our image's container. The observer monitors if the image enters the viewport using the entries intersecting condition. Upon intersection, we update isVisible to true and disconnect the observer to optimize performance by preventing unnecessary checks. During the initial render, if the image is not yet visible, a loading placeholder is displayed. Once it becomes visible, the actual image is rendered. This effective use of lazy loading not only enhances the user experience by deferring image loading, but also contributes to faster initial loading times, making it a valuable strategy in modern web development. As we wrap up our exploration of rendering patterns, it's essential to understand that these techniques contribute to enhanced performance, improved user experience, and overall application maintainability. Rendering patterns, whether client-side, server-side, or static generation, allow developers to craft applications that are not only fast to load, but also interactive and engaging. In conclusion, mastering these rendering techniques will enhance the performance of your applications significantly. As we've seen, choosing the right rendering strategy depends on the application requirements, user expectations, and specific use cases. Stay curious and keep experimenting with these concepts, as the landscape of web development is ever-changing, opening new doors for building efficient and engaging user interfaces. So far, we've covered a wide array of concepts from different rendering patterns to practical code examples that empower you to optimize your applications. Continue to explore these techniques as they are crucial for creating the next generation of high-performance web applications. With the evolution of web development, understanding how to generate and serve content efficiently is crucial. In this video, we'll explore the concepts of static rendering and server-side rendering, how they differ, and the implications they have for performance and user experience. So far, we learned about rendering patterns in web development, focusing on client-side rendering and its benefits for creating responsive applications. We discussed the PRPL pattern, code splitting, and the differences between server-side rendering, SSR, and static site generation, SSG, as strategies to enhance performance and user experience. We also explored hydration in server-ended apps and lazy loading techniques to optimize loading times further. Overall, these concepts are essential for building high-performance web applications. Now, we will talk about static rendering and server-side rendering in detail, understanding their use cases and advantages. In this code snippet, we define a functional React component for rendering a blog post that showcases the concept of static rendering in Next.js. The component, blog post, receives title and content as props and returns a structured HTML article layout. This makes it clear that when a user accesses a blog post, they will see the specified title and content immediately, enhancing user experience through fast load times. The key function in this setup is getStaticProps. It executes during the build time and is responsible for fetching the necessary data to populate our blog post. In this case, it simulates fetching a static post with a predefined title and content. When the application is built, this function generates the HTML page already populated with the fetched data, allowing users to access a fully rendered page without delays from API calls. This mechanism illustrates the efficiency of static rendering, as users can instantly view content upon navigating to the blog post, making it ideal for static sites where content does not change frequently. This approach not only improves performance, but also reduces the server load, showcasing the advantages of using static site generation with frameworks like Next.js. In this code snippet, we use Next.js to create a server-side rendered news article page. The news article component receives the article data as props and renders it inside an HTML article element, displaying the title and content dynamically. This structure allows users to view the latest article whenever they visit the page. The key feature here is the getServerSideProps function, which runs on the server for each request. This function fetches the latest news article from a specified API endpoint, ensuring that the content displayed is always current and relevant. It fetches the data and converts it from JSON format, making it accessible within the component. By returning the article as props, Next.js ensures that the data is seamlessly integrated into the rendered HTML. This method of server-side rendering is particularly effective for applications that require up-to-date information, such as news websites or e-commerce platforms. Overall, this approach exemplifies how dynamically generated content can enhance user experience by providing timely updates directly from the server. Both static rendering and server-side rendering have their respective advantages, and the choice between them often hinges on the specific use case. Static rendering guarantees high-performance loading times and is relatively simple to set up. The files produced are lightweight and can be easily cached by CDNs, which means they can be served quickly to users around the globe. On the flip side, server-side rendering offers versatility. By delivering up-to-date content immediately, it enables dynamic applications where data changes frequently. However, it also introduces overhead since the server is responsible for generating the content on each request. This may lead to increased server load and longer response times if not managed efficiently. When building applications, it's worthwhile to think about the type of content you will provide. If most of your content is static and changes infrequently, static rendering would benefit you by reducing server load and improving load times. For instance, marketing websites, documentation sites, or blogs are ideal candidates for static rendering since the content does not vary often. Conversely, if your application is news-based or includes user-generated content, SSR might be the right route. For instance, an e-commerce user dashboard that shows product availability or personalized recommendations benefits from server-side rendering. Imagine visiting a shopping site that has live stock updates. That freshness makes the shopping experience far more pleasant and ensures users always see the most relevant products. In the context of server-side rendering, SSR, with React, the hydration process is crucial to ensure interactivity after delivering fully rendered HTML to the browser. In this snippet, we use the React DOM hydrate method, which serves as the bridge between the server-rendered content and the client-side React application. The hydrate method takes two arguments. The first is the React component we want to render, in this case, my app, and the second is the DOM element where this component will be attached, identified by document, getElementById root. This method effectively attaches event listeners and prepares the application for user interactions, allowing it to function dynamically. By utilizing hydrate, we mitigate the risk of discrepancies between the server-rendered HTML and the expected HTML structure on the client side. This is essential because any mismatch can lead to unexpected behaviors, such as missing event handlers or incorrect UI states. Thus, mastering the hydration process helps create seamless and responsive web applications, enhancing user experience after the initial server response. Let's not forget about SEO implications as well. Search engines like Google can crawl statically rendered pages with ease, allowing them to index the content efficiently. This helps improve search rankings and visibility. Unlike client-side rendered applications, where the content is typically JavaScript rendered after a load, static site generators ensure that useful content is immediately available in the HTML that gets sent to search crawlers. On the other hand, SSR performs well for SEO purposes too, as it sends fully rendered pages to users and search engines alike. Dynamic content fetches happen right there on the server, so when a search engine bot visits a page, it sees the fully constructed HTML, improving the chances of ranking well in search results. In this section, we will dive into how to effectively implement caching in your server-side rendered applications to optimize performance. The code uses the setHeader method to define caching policies through the cache control response header. By setting cache control to public maxage equals 300, smaxage equals 600, you instruct the browser and any intermediary caches, like CDNs, about how to handle the cached data. The public directive allows the response to be cached by any cache, including public-facing caches. The maxage equals 300 specifies that the individual user's browser can store this response for up to 300 seconds before it needs to check back for a fresh version. Meanwhile, smaxage equals 600 tells shared caches, such as CDNs, that they can keep this response for up to 600 seconds, ensuring broader caching even for multiple users. This setup provides a balanced approach to maintaining performance while still being able to serve relatively fresh content. It reduces server load by minimizing the number of requests for unchanged content, while also ensuring users benefit from faster load times due to caching. Finally, a blend of both rendering methods can often be the best approach. For example, utilizing both static site generation for the majority of your content and server-side rendering for key dynamic pages can give you the best of both worlds. This hybrid approach allows you to serve fast, static content while still having the capability to present fresh data. Many modern frameworks, such as Next.js, make it relatively straightforward to combine these methodologies in a single application, which opens up numerous possibilities for optimizing user experiences. In conclusion, understanding static rendering and server-side rendering is crucial for any web developer. By knowing when to use each method, you can tailor your applications to suit your audience's needs. Whether you prioritize static speed or dynamic freshness, both rendering strategies have their place. By striking a balance between performance, user engagement, and search engine visibility, you can elevate your web applications to new heights. So dive in, experiment with these techniques, and build web experiences that not only meet but exceed user expectations. In this segment, we're diving into the exciting world of hybrid rendering, a modern web development approach that combines different rendering techniques to enhance user experience and performance. So far, we learned about static rendering and server-side rendering in web development, highlighting their key differences and use cases. We discussed how static rendering generates HTML at build time for fast loading, while server-side rendering delivers dynamic content that updates with each request. The importance of considering performance, user experience, and SEO when choosing between these methods was emphasized. Additionally, we explored caching strategies and the benefits of combining both approaches to optimize web applications. Now, we will talk about hybrid rendering, how it conceptually challenges traditional terminology, and why it emphasizes new verbiage in the context of modern web practices. Hybrid rendering is transforming how we think about web applications. Traditionally, we've categorized applications as single-page applications, SPAs, multi-page applications, MPAs, server-side rendering, SSR, or static site generation, SSG. However, as web technologies evolve, these definitions become overly simplistic and somewhat limiting. In hybrid rendering, we blend these approaches to create solutions tailored for specific use cases, providing a more nuanced understanding of the ever-changing web development landscape. In this example, we have a React component designed to illustrate hybrid rendering using Next.js, showcasing both static and server-rendered content. The homepage component takes latest products as a prop, which is rendered in a list format. The key aspects of the code involve two data fetching functions. The getStaticProps function fetches static information, such as site-wide data, from an external API and provides it as props to the component, enabling fast initial load times. By using this method, users can quickly access essential static content without experiencing significant delays. On the other hand, getServerSideProps is used to gather dynamic data, specifically the latest product offerings. This function executes on each request, ensuring that users always see the most current product listings. The beauty of this hybrid approach lies in its seamless integration of static and dynamic rendering, allowing core components of the web page to load promptly while still updating critical information regularly. This combination ensures both performance benefits and a responsive user experience. In this code segment, we focus on implementing a caching strategy for dynamically fetched content using Redux in a hybrid rendering setup. First, we establish a connection to the Redux client, enabling us to store and retrieve cached data efficiently. The getServerSideProps function is crucial here. It's executed on each request to fetch the latest products. At the beginning of the function, we define a cache key, latest products, and attempt to retrieve any cached data associated with it. If cached data exists, we pause it and immediately return it as props for our component, allowing us to serve this data without incurring additional API calls. This significantly reduces server load and improves response times. However, if no cached data is found or if it has expired, we initiate a fetch request to an API endpoint to retrieve the latest products. Once we obtain this data, we store it in Redux using the setX method, setting an expiration time of 1 hour. This allows us to strike a balance between delivering fresh content and optimizing performance. Ultimately, the approach blends static and dynamic rendering strategies, maintaining a seamless user experience. In this section, we'll look at how the loading spinner component and the modified homepage integrate user feedback into our hybrid rendering application. The loading spinner component serves as a visual cue for users while content, specifically the latest products, is being fetched. It creates a simple, animated spinner using styled JSX to enhance the user experience. The CSS applied here ensures that the spinner has a circular shape and rotates indefinitely, providing a smooth loading indication. In the homepage component, we introduce an isLoading flag, which dictates whether to display the spinner or the actual product list. When isLoading is true, the loading spinner is rendered, keeping users engaged while they wait for data. Once the data is loaded and the flag is false, we execute a loop to display the fetched products in a list format. This approach highlights the importance of providing visual feedback in hybrid rendering applications. By ensuring users are aware of ongoing processes, we maintain a seamless experience even when some content loads at different speeds. Embracing hybrid rendering offers an excellent opportunity for developers to break free from conventional categorization and instead focus on delivering superior user experiences. By creatively merging the strengths of static and dynamic rendering, we can craft application architectures that scale efficiently while remaining responsive to user demands. As we've explored, blending rendering methods both enhances performance and ensures that essential content remains up to date, directly addressing users' needs while keeping load times minimal. Imagine a scenario where users are greeted with an immersive experience that feels instantaneous yet features live data, a sweet spot for any application. However, hybrid rendering is not without its challenges. Developers must remain vigilant about the complexities of managing cache strategies, ensuring smooth interactions, and analyzing performance metrics to decide the optimal approach. Regular testing and user feedback will help guide the evolution of these applications, making them continually better over time. Before we conclude, it's worth mentioning the growing importance of accessibility and inclusivity in design practices across any rendering strategy. Ensuring that your content is accessible to all users, regardless of ability or environment, should always be a primary consideration. This applies equally to static and dynamically rendered content, and utilizing tools and best practices in hybrid rendering ensures you can serve diverse audiences effectively. Winding down, the world of hybrid rendering is not just a trend. It's a natural evolution of how web applications should function for end users. As you embark on your journey in building modern applications, consider where hybrid rendering can fit into your toolset. By embracing the best of both static and dynamic worlds, you equip yourself with the ability to create applications that not only meet today's standards, but set new ones for tomorrow. Now go out there, experiment, and build some amazing applications that redefine user experiences using the power of hybrid rendering. Building software applications is an exciting journey, especially with modern frameworks like React.js. In today's tutorial, we're diving into a crucial aspect of application development, application structure. Organizing your code is not just a matter of keeping things tidy. It's about creating a solid foundation for your project that scales effectively as you grow. So far, we have learned about hybrid rendering in web development, which combines various rendering techniques to optimize user experience and performance. We discussed the limitations of static and server-side rendering and how hybrid rendering addresses their challenges by blending static and dynamic content according to specific needs. Emphasizing the importance of cache management, user engagement, and accessibility, we explored how this approach enhances application responsiveness while delivering up-to-date information seamlessly. Overall, hybrid rendering represents a significant evolution in creating modern web applications that cater to diverse user demands. Now, we will talk about application structure and how to organize your project files effectively. When building small hobby projects or trying a new library, it's quite common for developers to start throwing files into a single folder without any real plan. This might work in the beginning, but as your project starts to accumulate files, assets like CSS, helper components, images, and pages, it quickly becomes unmanageable. A structured approach to your applications files can save you time, sanity, and ultimately make your project easier to maintain. In the provided project structure, we can observe a clean and organized hierarchy that facilitates navigation and understanding of the application. The public folder contains essential static files such as index, HTML, which serves as the entry point for the application, and favicon, ICO, which is used for the browser tab icon. Moving into the src folder, which houses the core functionality of the application, we see dedicated subdirectories for components and pages. The Components folder is designed to store reusable components, such as header, JS, and footer, JS, that can be used throughout different sections of the application, promoting reusability and consistency. Meanwhile, the Pages directory includes components that correspond to various views or screens in the app, like Homepage, JS, and About Page, JS. This clear separation helps developers locate relevant files based on their purpose, ultimately enhancing collaboration and easing debugging. By structuring files in this way, development becomes more efficient, laying a solid foundation for future growth. In this feature-based application structure, we can see that the src folder is organized around distinct functionalities. Each feature gets its own dedicated folder, such as auth and profile. This not only encapsulates related files together, but also enhances maintainability and clarity. For instance, within the auth folder, there are two key components, login, JS, and signup, JS, which handle the user authentication process. The auth styles, CSS, file provides styles specific to these components, ensuring a cohesive look and feel. Similarly, the profile folder contains profile page, JS, which likely renders user profile information, along with profile styles, CSS, for styling. By structuring the project this way, developers can easily locate and modify files related to a specific feature, making debugging simpler when issues arise. This approach fosters a logical flow in the codebase, allowing teams to work more efficiently, especially in larger applications where clarity is paramount. Ultimately, organizing files by feature not only streamlines development, but also helps keep the project scalable as new functionalities are added. In this section, we delve into a straightforward implementation of a login component designed to encapsulate all related functionality within the auth folder. The component utilizes React's useState hook to manage local state for the username and password inputs. This allows for controlled components, where the state of the input fields is directly tied to the component's state. When a user fills out the form and submits it, the handle submit function is triggered. This function first prevents the default form submission behavior and then logs the provided username and password to the console, where you can implement the actual login logic later. The structure of the rendered output consists of a div container that houses an H2 heading for the login title followed by a form element. Within this form, there are two input fields, one for the username and another for the password. Each input field updates its respective state on change, ensuring that the component always reflects the latest user input. Finally, a button is provided for submitting the form. This organization not only creates clarity within the code, but also enhances the maintainability of the login functionality in the context of the overall application structure. In the previous section, we discussed implementing a hybrid folder structure for your application to balance reusability and feature encapsulation. Now, let's delve into the specific organization of files within this structure. The code reflects a project hierarchy that includes both shared components and specific feature folders. Under the SRC directory, the Components folder contains reusable UI elements such as button, JS, and modal, JS, which can be utilized across various parts of the application, enhancing maintainability and preventing duplication. Additionally, the unique functionality of the application is encapsulated within individual folders, such as auth and profile. The auth folder includes the login, JS component, which handles user authentication, while the profile folder contains the profile page, JS, to manage user-related data. This hybrid structure not only promotes code reusability, but also organizes functionality logically, allowing developers to locate and manage files efficiently. As your application grows, this organization helps streamlining updates and debugging processes, ensuring that related files are easily accessible and modifications are more straightforward. By following this approach, you're setting a solid foundation for future scalability. In the auth slice, JS, we leverage the Redux toolkit to manage the state and actions pertaining to user authentication. By defining our slice, we establish a clear structure for the authentication logic, organizing it logically within the auth folder. The createSlice function is called to initiate the slice, where we specify the name, initial state, and reduces. In this instance, the initial state represents whether a user is authenticated, starting as false. The reduces defined, login, and logout are functions that modify the state in response to specific actions. When a user logs in, the login reducer updates the isAuthenticated state to true, while the logout reducer resets it back to false. This clear separation of concerns aids maintainability, allowing developers to easily locate and modify authentication-related logic. Additionally, by exporting the actions, login and logout, along with the reducer, other parts of the application can seamlessly dispatch these actions to update the authentication state, ensuring that the UI reflects the user's current login status effectively. In this Redux setup, we create an auth slice that holds the initial state of authentication and includes reduces for login and logout actions. This approach keeps your authentication logic centralized within the auth folder, promoting organization and maintainability. Finally, let's briefly discuss best practices when working with application structure. One helpful tip is to use meaningful naming conventions for your folders and files. This clarity aids not only your future self, but also others who might collaborate on your project later. Additionally, consider utilizing code linters and formatters to maintain a uniform code style across your files. Another crucial aspect is to document your structure. A simple README file at the root of your project could explain the reasoning behind your organizational choices, making it easier for other developers to onboard quickly or if you revisit the project after some time. In summary, understanding and utilizing an organized application structure is essential in developing scalable and maintainable projects. We explored various methods for structuring files, grouping by feature, by file type, and employing a hybrid approach that takes the best from both worlds. By focusing on organization, documentation, and thoughtful conventions, you ensure that your code base remains clean and accessible. As we wrap up this lesson, remember that the structure should serve your development needs, adapting as necessary for project growth and team collaboration. Stay tuned for our next session, where we'll explore advanced state management techniques in React applications. Happy coding! When developing React applications, organizing your files efficiently is crucial for maintaining coding productivity and overall project manageability. Today, we will dive into the two primary ways to group files in a React application: grouping by feature and grouping by type. So far, we learned about the importance of organizing application structure to ensure coding efficiency and maintainability. We discussed various methods for structuring files, including grouping by feature and adopting a hybrid approach that combines both feature-based and type-based organization. Emphasizing meaningful naming conventions and documentation, we highlighted how a well-structured codebase promotes collaboration and accessibility. In our next lesson, we will delve into advanced state management techniques in React applications. In this example, we will dive into the structure of a React application that is organized around features, specifically focusing on the authentication module. The auth folder contains three vital components: login.js, signup.js, and auth styles, CSS. Each JavaScript file represents a distinct part of the authentication process, with login.js handling user login and signup.js likely facilitating user registration. The login.js component utilizes React's built-in useState hook to manage the state for username and password inputs, enabling dynamic interaction as users type. The form submission leverages a simple event handler that prevents the page from refreshing and logs the username, indicating where the authentication logic would ultimately be implemented. Moreover, the associated CSS file, auth styles, CSS, is crucial for defining the visual presentation specific to the authentication feature, keeping the styling encapsulated within the auth context. This organized approach not only enhances productivity by allowing direct access to all related files, but also streamlines code management as the application scales. Each feature folder thus becomes a self-contained module, promoting clarity and ease of development. In this section, we will explore the login component, which is crucial for managing user authentication in our application. The component starts by importing necessary libraries, including React and the useState hook, which allows us to manage state within the functional component. The login function initializes two pieces of state: username and password, both of which are set to empty strings initially. As users input their credentials, the setUsername and setPassword functions update these state variables accordingly through controlled form inputs, ensuring that the user experience is smooth and responsive. The handleSubmit function prevents the default form submission behavior, capturing the entered username and potentially logging it, although the actual login logic is yet to be implemented. The component returns a simple yet structured login form wrapped in a div with a designated class for styling. It includes two input fields for users to enter their username and password, along with a submit button that triggers the handleSubmit function. This encapsulation of functionality and state management within the auth folder exemplifies how feature-based organization enhances maintainability and clarity in our application. In the type-based organizational structure, we have a header.js component that plays a crucial role in the navigation of our social media application. This component is designed to render the application's header, which includes a title and links to various pages such as home, login, and signup. By importing React and the link component from React.ru.dom, we ensure smooth navigation between different routes of the app. The component also imports a CSS file, header.css, to style the header, emphasizing the importance of keeping styles organized separately. In the rendering part, the header section is wrapped in a header tag for semantic clarity, and it contains an H1 element that displays the app's name, providing a clear identity for the application. Additionally, the navigation links are created using the link component, which allows users to transition between different pages without a full page refresh, enhancing the overall user experience. This structure illustrates how components can be simply organized by their function, even though it may lead to challenges when tracking interactions across features, as noted previously. In the following code snippet, we have a simple yet effective implementation of a header component using React. This component serves as a fundamental navigational component for our social media application. The code begins by importing necessary modules, including React itself, the link component from React for navigation, and a CSS file for styling. The functional component header is then defined, which returns JSX that structures the header UI. Inside the header, there's an H1 that displays the title of the application, Social Media App. Following that, a nav element holds several link components that function as navigation links, directing users to the home page, login page, and sign-up page. This approach facilitates seamless navigation within the app, allowing users to access various parts quickly. However, as noted, the separation of the header component from the auth feature can create challenges in managing related functionalities, especially when adjusting link behavior based on the authentication state. This situation exemplifies the complexities that may arise when using a type-based organization without considering the contextual relationships of components. In this segment, we will discuss the hybrid approach to organizing a React application, which combines both feature-driven and type-based structures for maximum efficiency and clarity. The provided code structure exemplifies this strategy by organizing shared components, such as the button and modal, in a common directory named components. This ensures that these widely used elements are easily accessible throughout the application. Additionally, the specific features like user authentication and posts have their own directories, containing related components like login, signup, post feed, and create post. This encapsulation allows developers to work on individual features without searching through unrelated code, improving productivity. For instance, when handling user interactions, the modal component can be reused across various contexts, making the interface consistent and saving development time. By storing shared components together while keeping feature-specific functionality organized, developers can enjoy a clean and manageable codebase. This approach fosters collaboration, as team members can quickly locate and understand the relevant components needed for their tasks, significantly enhancing the development workflow. In this section, we will break down the implementation of the modal component, a reusable UI element that can enhance user interaction across various parts of your application. The component begins by importing necessary dependencies, specifically React and the associated CSS file for styling. It takes in 3 props: isOpen, onClose, and children. The isOpen prop determines the visibility of the modal. If it's false, the component returns null, effectively rendering nothing to the screen. This condition is critical for controlling the modal's display state without unnecessary renderings. When the modal is open, it returns a structured JSX layout with an overlay and modal content area. The overlay serves as a backdrop, dimming the main application behind the modal, enhancing focus on the content displayed. Within the modal, there's a close button that triggers the onClose function, allowing users to dismiss it easily. The children prop is utilized to dynamically render whatever content is passed to the modal, making it highly versatile. This pattern results in a clean, functional, and reusable component that can be integrated seamlessly throughout your app, wherever a modal interface is needed. Regardless of whether you choose to group your files by feature, type, or blend both strategies, one universal truth remains. Clarity and organization lead to improved collaboration and reduced frustrations. It's incredibly important to consider meaningful file naming conventions and documentation so team members can jump in and grasp the structure at a glance. This adaptation is particularly beneficial when working in a team setting, as it leads to seamless collaboration and understanding among developers. Consider making it a habit to add a README file at the root of your project, providing a quick overview of your file organization. A well-documented project helps onboard new developers and guide them through your architecture and thought process. As we wrap this up, always remember the fundamental principle behind organizing your codebase is not to make it aesthetically pleasing, but to enhance maintainability and understandability. Regardless of how advanced your application becomes, the organization will be the foundation upon which it thrives. Whether you're collaborating with a team or flying solo, controlling your application's code organization will empower you to move faster, solve problems more easily, and manage changes effectively. With proper file structuring, you can build upon your React applications confidently. In our next lesson, we will explore advanced state management techniques in React applications. This will be an exciting deep dive into managing application state more effectively. Modern React applications leverage a variety of powerful features like Redux, stateful containers, hooks, and styled components to enhance their functionality and maintainability. With these tools, we can create dynamic user interfaces that are not only efficient, but also easy to manage and scale. In this section, we will explore how to set up Redux in your React application. First, you'll need to install Redux and React Redux using npm, which provides the necessary tools to manage application state effectively. Once installed, the next step is to create a Redux store. The store is a centralized repository for the application state. We define some action types, specifically increment and decrement, representing what actions can be performed to alter the state. Action creators are functions that create these actions. In our case, the increment and decrement functions return objects with the corresponding action types. The reducer function is crucial as it dictates how the state transitions in response to these actions. Here, we initialize the state with a count set to 0. The reducer listens for actions and updates the state accordingly. It increases the count when the increment action is dispatched and decreases it for the decrement action. Lastly, we use the createStar method to instantiate the star with our defined reducer, thereby organizing the state management structure of our application. In this section, we connect our Redux star to a React component using the provider from the React Redux library. We define a counter component that utilizes the uselector hook to retrieve the current count from the Redux star's state, ensuring that our component always reflects the latest state. The useDispatch hook provides us with the dispatch function, allowing us to send actions to update the state when the user interacts with the component. As the user clicks the increment or decrement buttons, the appropriate action is dispatched, triggering a state change in the star. This update causes React to re-render the component, displaying the new count. Wrapping the counter component in the provider ensures that it has access to the star, thereby enabling a seamless flow of data and state management throughout our application. This pattern not only streamlines the connection between state and UI, but also promotes better organization and maintainability of code, crucial in building scalable React applications. In this segment, we will explore the shopping list container, a stateful container component designed to manage a shopping list state. The shopping list container uses the useState hook to create a piece of state called items, initialized with a few fruit names. This state holds the list of items in the shopping list and can be updated using the setItems function. The container also defines an addItem function that takes a new item as an argument. Within this function, setItems is called with an updated array that includes all previous items plus the new one, showcasing the fundamental practice of immutability in state updates. The shopping list presentational component is then rendered, receiving items and addItem as props. This design emphasizes the separation of logic and presentation, allowing shopping list to focus solely on rendering the UI while shopping list container handles the data. As a result, this architecture promotes better maintainability and clarity. By structuring your components in this way, you ensure that each component has a distinct responsibility, making your application easier to understand and extend. The shopping list component is designed to manage and display a dynamic list of shopping items. It takes in items and addItem as props, with items representing the current list and addItem being a function to add new items to this list. Inside the component, we define a handle addItem function that is triggered when the Add Item button is clicked. This function prompts the user to enter a new item. If the user provides an input, the addItem function is called to update the list. The return statement of the component renders a simple UI that consists of a heading, an unordered list displaying the current items, and a button for adding new items. Each list item is uniquely identified using its index as the key prop, which enhances rendering performance in React by helping the library identify which items have changed, been added, or removed. This structure emphasizes a clean separation of concerns, allowing for easy management of state and presentation, which is crucial for maintaining larger applications effectively. Let's explore the custom useFormInput hook, designed to streamline form input management in React applications. This hook initializes state using the useState hook, taking an initial value as an argument to set the default value for the input field. Inside the hook, a function named handleChange is defined, which updates the state whenever the input changes by capturing the event and setting the new value. The beauty of this custom hook lies in its simplicity and reusability. By returning an object that exposes both the current value and the onChange handler, any input component can easily integrate it. Instead of writing repetitive state management code for each input in a form, you can simply invoke this hook for as many inputs as needed, keeping your components clean and reducing boilerplate. This modular approach enhances maintainability and readability, allowing developers to focus on building user interfaces without getting bogged down by repeated state logic for form elements. Using custom hooks like useFormInput exemplifies best practices in React by promoting code reuse and organizing functionalities efficiently. In this section, we demonstrate how to utilize a custom hook, useFormInput, within a React functional component to manage form state efficiently. The form component starts by importing React and the custom hook, which allows for streamlined state management of input fields. Within the component, we declare two instances of useFormInput, one for the name field and another for the email field, both initialized with empty strings. This setup enables us to easily handle the input values as they change. The handleSubmit function is defined to prevent the default form submission behavior, allowing us to capture the current values of the name and email fields for logging or further processing. In the JSX return, the component renders a form containing labeled input fields. By spreading the returned object from the useFormInput hook into the input elements, we bind their values and the change handler directly to the respective fields. This approach eliminates the need for additional state management code typically required in forms, promoting cleaner and more maintainable code. Finally, a submit button is included to trigger the form submission. Another powerful tool we can incorporate in our React applications is styled components, which enhances how we style elements within our components. To utilize styled components, the first step is to install the library using npm, which allows you to easily manage and incorporate the styles. After installation, we can import the styled object from the library, which provides a way to create styled elements. In our example, we define a styled button that is actually a styled version of the standard button HTML element. This styled button uses template literals to include dynamic styles based on props passed to it. Specifically, the background color changes depending on whether the primary prop is true or false, allowing for versatile button designs. In addition to the dynamic background, we also set standard styling for the button, such as the text color, padding, border radius, and cursor properties. Lastly, we incorporate a hover effect that adjusts the opacity, enhancing the user experience. Utilizing styled components in this manner helps ensure styles are scoped exclusively to the components, promoting a clean and maintainable codebase. In this section of the tutorial, we showcase the integration of styled components within a React application. The app component serves as the main entry point where two instances of styled button are rendered. The first button is assigned the primary prop, which applies a blue background to it, highlighting its importance. Therefore, it stands out visually for primary actions. In contrast, the second button does not receive any prop, resulting in a default gray background, which indicates a secondary or less prominent action. This approach of defining styles directly within the component structure promotes modularity and encapsulation. By utilizing styled components, developers can define the button's styling, such as color, padding, and hover effects, in a way that is directly tied to the component itself. This encapsulation of styles ensures that they do not clash with other styles in the application, enhancing maintainability. Moreover, it exemplifies the CSS and JS methodology, which allows for dynamic styling based on props, making it exceptionally versatile for varied UI scenarios. Overall, this example emphasizes the streamlined styling process in modern React applications and encourages developers to adopt styled components for better design consistency. As we reflect on everything we've covered today, it's clear that these advanced structuring practices using Redux, stateful containers, hooks, and styled components considerably enhance the way we develop modern React applications. By utilizing Redux, we manage state elegantly across our application while maintaining predictability. Stateful containers help separate logic from presentation, fostering easier maintainability. Hooks give us flexibility and reusability when managing state and effects, and custom hooks further simplify our components' code. Lastly, styled components allow us to style our applications in a scoped and dynamic fashion, making CSS management intuitive. Remember, choosing the right combination of these features will depend on the complexity of the application you're building and your team's preferences. Experimenting with these advanced practices will empower you to create robust, scalable, and maintainable React applications. Thank you for joining me in this deep dive into advanced structuring practices in React. In our next session, we will explore even more about performance optimization techniques in React applications. Stay tuned.